Actually, okay. Cool.
I'll welcome people and I'll introduce you. Good morning, everyone. Good morning. Welcome to the mini symposium for computational chemistry and material science. My name is Ray. I'm a postdoc from Washington University in St. Louis. It's my great pleasure to chair this session and also welcome you to this first session of our mini symposium. Before we get started, I would like to acknowledge our supporting sponsors, the Carnegie Mellon Department of Chemistry, and also the Material Science and Engineering, as well as the JuliaCon community for initializing this mini. Of course, thank you all for coming to JuliaCon and then stay until the last day. It's my great pleasure to introduce our first speaker, Leticia. Yeah, and talking about computational quantum chemistry with sparse matrix algorithm. Please take it. And sorry for the other speakers, I will remind you at 10 minutes mark before your 30 minutes total length. So that means you have 10 minutes to wrap up and answer questions if there are any. All right, thank you, Leticia.
Thank you so much for the introduction. So I'm Leticia, and I'm going to disappoint you in the first minute of the talk because in the schedule and everything and on my slide, it says computational quantum chemistry with sparse matrix algorithms, but there was a last minute change, and the real title of my talk is computational quantum chemistry with stability analysis of wave functions. So it's a different approach, and I will explain what I'm doing to perform stability analysis of wave functions using stability matrices and how we build them with Julia. So I'm a PhD student at Carnegie Mellon University in the chemistry department. Here's my GitHub profile. My email and information are there. My main research areas are catalysis, polymerization, and physical chemistry for polymerization, quantum chemistry, investigation of electron-electron correlation with different ab initio and density functional theory methods, and also analysis of chemical bonding with analysis of a wave function. So the outline of my talk, it looks like a lot that we'll be talking about today, but I will actually be showing a bunch of examples of what I'm doing. So the first part of my talk, I'll be introducing to the problem of bond dissociation in chemistry, why are bond dissociation scans relevant, the concept of instability in potential energy curves, and then I will show some examples of bond dissociation in diatomic molecules, where does DFT fail, and where does stability analysis come into play to try to address and resolve problems that we encounter when we perform bond dissociation scans and we try to break bonds computationally with the quantum chemistry methods that we have available. And then I will show how to integrate stability analysis of wave functions with geometry optimization, and we'll expand stability analysis to small molecules. So we'll not only talk about bond breaking by stretching, but also bond breaking by torsional scans. And then I will show one example of this. And as future work, I want to expand this approach to chemical reactions to study transition states and apply to larger systems like and more complex bonds like in coordination chemistry or transition metal complexes. Okay, so the first thing I want to address is why do we care about breaking bonds, right? And why do we care about bond dissociation scans? These are important to analyze amongst everything: molecular structure, spectra, bond energies, conformation energies, reaction barrier heights, vibrational frequencies, and much more. That's what we can obtain when we calculate the potential energy curve of a chemical bond. So the first thing is, if you're not familiar with potential energy curves, I have one example here. And suppose you have a molecule with atoms or fragments AB, and then you form a bond between these atoms or fragments. And you are breaking it. So in your x-axis, you have the distance between the fragments or atoms. When you are at the minima, you have the equilibrium distance. So you say that the bond is stable, you have a bond formed there. And then when you pull it apart, when you pull the fragments apart from each other, you dissociate the bond, and then you have this flat curve. And this all happens when we are considering homolytic cleavage. So when you dissociate, you form open shell species. And when you have a stable bond, you have closed shell species. And the difference in energy between the minima and the energy of the dissociation is considered, it's called the bond dissociation energy, which can be corrected with thermodynamic calculations for 0-point corrections as well. Okay, so from an electron density perspective, I'm showing here that when you have a stable bond, you have this whole density shared across the molecule and mainly centered in the bonding region. And then when you dissociate, you have part of the density localized in one atom or fragment, and the other part of the density localized on the other fragment or atom, right? So you have two open shell species that have this density when the bond is dissociated. Okay, so I will start with the simplest model, hydrogen, our hydrogen molecule. So let's use DFT to break this bond. Experimentally, the bond dissociation energy, the delta E to break this bond is 106.13 kilocalories per mole. But when you use DFT, and here I'm disclosing the level of theory, and we can talk about other levels of theory. When we talk about DFT, the same behavior is observed for other functionals as well. So you overestimate the BDE for the hydrogen molecule, as you can see. And you overestimate by a lot, by 76 kilocalories per mole. So what's wrong with DFT? This is like a decent level of theory, but still. And I'm running an unrestricted calculation, so what's going on? So here, looking at the density, looking at the density of alpha and beta bonding orbitals, you can see that as you dissociate, instead of having half of the density on alpha, half of the density on beta, so you have one electron and one localized in one atom, the other one localized on the other atom, you have this kind of half and half. So for your alpha bonding orbital, when you dissociate, you have half of the density in one atom, half of the density on the other atom. And for beta, the same happens. And that's not an accurate picture. As I showed before, you should have half of the density on one atom and half of the density on the other atom. So we see that's why this is being overestimated, because if you look at this density, and if this is happening, it means that it's overestimating how much bonding character you have on that interaction, even when you dissociate the bonds. And one of the approaches that people commonly use to resolve this issue is by performing symmetry breaking. So you mix the density of HOMO and LUMO. So you mix the density of your lowest unoccupied molecular orbital, and you break the density when you approach the degeneracy limit and you are breaking that bond. And this allows you to kind of resolve that, that overestimation issue. So this is just a summary of what this symmetry breaking approach means. You are mixing HOMO and LUMO most of the time, right? But there is an issue. Here we are talking about hydrogen molecule. So your HOMO is your bonding orbital, and your LUMO is your anti-bonding orbital. So this mixing works pretty well. However, if your HOMO and LUMO do not correspond to bonding and anti-bonding, this approach to break the symmetry by mixing these densities does not work. And I'll give you a simple example. Difluorine. I'm not going to go over all the examples that I have, and like at some point we can talk about those. But if you look at the HOMO for difluorine, you have a lone pair from one of the p orbitals. They're not bound. So what happens is you can't just mix the non-bonding orbital when you break the symmetry. It's not going to resolve this overestimation issue, which happens across the board on DFT, right? So just to show, this is what people commonly do, and it will work for hydrogen, but as I said, it's not an approach that can be easily used across the board, right? So going back to our potential energy curve, the most critical region of the potential energy curve is this one. When you go from a closed shell, again, considering a homolytic cleavage, when you go from a closed shell species to open shell species, you generate this instability. You can't determine the spin multiplicity very well because you are on the verge of breaking that bond. So you are forming unrestricted, you're forming open shell species. So you don't know in your calculation if it should be unrestricted or restricted, right? So let's call this for pedagogical purposes, instability and instability region. So, okay, going back to our hydrogen molecule, and we'll go to more complicated systems later, I promise. I used the black curve, which you cannot see. I used a gas mix in Gaussian, which means that I was mixing HOMO and LUMO, and I was performing the broken symmetry thing. And on top of it, you'll see the red curve. So they are overlaid because they give you the same result. And the red curve is the stability analysis, right? And I'll explain what stability analysis means. So I found an approach that can work just as well as breaking the symmetry and can be applied in a broader context, so to more molecules. And that's why you can see the black curve behind the red curve. But that's the idea here. For hydrogen, broken symmetry works, but then I found this approach which is broader and allows us to perform bond breaking in more systems. So let's look at the density again and correct our picture, right? So now you can see that when you break the bond, half of the density will be in one atom, half of the density on the other atom. So you broke that bond. That's why you corrected the bond association energy. And it matches the experiment much better now. Okay. So what is this great thing that I called stability analysis? So stability analysis is not something I invented, right? Actually, it was published for the first time on the 50s. And people were talking about, oh, very difficult to converge molecules. So they were talking about polyenes, conjugated polymers, conjugated systems, which we know the self-consistent field analysis of those systems, it is quite challenging, and it takes a while to converge them. Because you have delocalization of electrons, and you have a lot of degenerate states, which makes it very hard to find the lowest energy. So what did I do? First, I will define what stability is, right? So the SCF stability will give an indication whether the SCF solution is at a local minimum or a saddle point. And it tests the stability of Hartree-Fock or DFT wave function by Comshan analysis, right? Constant theory, and considering a single determinant wave function with respect to relaxing various constraints. This include allowing the restricted determinant to become unrestricted, so you will resolve that instability by going from restricted to unrestricted. You can allow orbitals to become complex. You can reduce the symmetry of the orbitals as well to reduce this issue related to degeneracy. And the whole idea is that you will build an electronic Hessian. What do I mean by electronic Hessian? So you are going to perform orbital rotations. So you are going to do and build a matrix just as a CISD matrix with all singles and doubles excitations. And this will be your electronic Hessian. And then you are going to calculate the eigenvalues of that Hessian. And the requirement for the stability is that the eigenvalues of this matrix would be positive. If you find positive eigenvalues, then your wave function is stable with respect to those orbital rotations. But if you find one negative eigenvalue with respect to a specific orbital rotation, this means that you have to mix those orbitals to resolve that instability. All right? So that's the whole idea. And then when you find the instability, you can resolve it by performing a 1D search. And this method is implemented in Gaussian, is implemented in Orca, is implemented in many softwares. So what I did, first, to learn how this method worked, and two, to optimize and make it faster, I implemented this method in Julia. So I will just go over a simplified version of the code just to show. I'm not going to run a tutorial. I'm just going to show like in more detail the steps with a simplified version of the code. Just allow me 1 second to pull up my VS Code. Okay, so idea, and I'll go over this quickly. The idea is that I will post-process molecular orbital energies, molecular orbital coefficients, and the molecular integrals that you get from Orca, Gaussian, or in this case, Orca, which is the software that I use in most of the cases. I will extract those things from the output. I will build this electronic Hessian by performing these orbital rotations. I will calculate the eigenvalues and eigenvectors, and then I will detect the instability by checking the signs of these eigenvalues, and then I will perform a 1D search to optimize in case an instability is found, and then I can just return the density that I get. I can just return to Orca or Gaussian, and then rerun the calculation with a stable density. So use a stable density as an initial guess for my calculation. So that's the whole idea of my implementation in Julia of stability analysis. Okay, so now we talked about very simple molecule, dihydrogen. So we have this great example, but I showed you that breaking the symmetry works for hydrogen, right? So what about other molecules? Dinitrogen. So for those of you who work with bond dissociation, it's a little bit scary, dinitrogen. We have to break 3 bonds, so we do need multi-reference character. We do need a not only multi-reference, but multi-determinant also approach to resolve this issue and break this bond. So I tested a bunch of different methods. So let's just start with Hartree-Fock. I always like to start with Hartree-Fock because no correlation. We just see like how the method performs here. So Hartree-Fock is this blue curve you see, highly overestimated. And then you see you add multi-reference characters, so Hartree-Fock with a Cas-SCF procedure. You see that you improve a little bit compared to what the experiment is. And then you add stability analysis. You do resolve some of the static correlation problem here. Of course, the bond association energy, because it's hard to fuck, the bond association energy is low still, but you do resolve some of the static correlation problems, so you can actually break the bond and you resolve some of the overestimation that you find with hard to fuck. Very interesting. So let's add some dynamic correlation and see what happens. So I tested MP2, CCSDT. We can see no static correlation, doesn't work. These are still single reference methods. To break a triple bond, no, not good. And then I tested some methods available in Orca called NVPT2, CAS-SCF. So you have dynamic and static correlation. They predict the bond association quite well. So, okay, what if I use DFT with stability analysis? Ta-da! Here. So we have DFT with stability analysis. It's just right on the money. It's just predicting the correct bond association energy, even with DFT. So you can break a triple bond using stability analysis with DFT, which is much lower cost than using these expensive multi-reference methods. And it just works pretty well with DFT. And the fact that I implemented in Julia, I'm not going to go over benchmarks and everything. This is something that will be on the documentation of the package, and it will be on the paper later. But the fact that I implemented in Julia made it easier to post-process everything and perform the stability analysis, because I simplified the procedure quite a bit compared to like Gaussian and Orca. Okay. So another thing that we can do, so we took this stability analysis calculation, right? Triple bond, let's detect where am I breaking the bonds specifically. So just showing you along the potential energy curve, you can see specifically at what point you broke each one of the bonds in nitrogen. So take the density, and then you just visualize the bonds that are being broken here. Okay, this method is great. People have been using it for some things related to convergence of conjugated systems, as I said, and they explored, oh, let's do stability in this perspective with Hartree-Fock, with Conshan, complex, and whatever. But why is it not more like spread out or used beyond the atomic molecules? Because we can't perform geometry optimization calculations with this current implementation. So my next step, integrate stability analysis with geometry optimization. So here, simplifying a little bit what I'm doing to optimize. What I do, I perform a DFT calculation, so I have an optimized structure. I perform the stability analysis on that, and then by performing the stability analysis on that, I use the stable density as an initial guess for my optimization with DFT again. So I have two different methods here that I proposed. The other one would be at each cycle of the optimization, check for stability, but this method is much more costly. So for now, method one, right? And there are some questions still that I want to answer with method one. So how does optimization with the stability analysis change convergence? That's something I want to study as well. How does optimization with the stability analysis change structure when it's expanded to much larger structures? So I selected some small molecules. I'm not going to show all the examples here for the sake of time, but I will show some of the most interesting cases using this method. So first, let's go to CC series. Let's break CC single bond on ethane first. And you can see that, I know, just butyryl IP, just for testing, you can break this bond, and it's quite close to the experimental value when you use stability analysis with DFT. Very nice. Now, a little bit more complicated case, ethylene. And the complication of this case is the following. When you break ethylene, you form two methylene radicals, right? And then you have to account for that, and then you have to properly predict the spin multiplicities of your product. So I ran calculations for singlet, triplet, and quintet. And we know that when the bond breaks, the whole system is a quintet because you have two triplets, right? So you can see here that it converges at the end to a quintet. And another thing, with this calculation, we can actually predict what's the singlet triplet gap for methylene radical, which is something that in quantum chemistry literature we know that people have been trying to do for quite a long time, and different methods and multi-reference character and all this electronic structure drama happening here. So with the stability analysis, just using simple functional B3LIP, I got a quite reasonable gap compared to other methods. So 2 times 7.5, so the gap for individual species is 7.5 kilocalorie per mole compared to the experimental value of 9 kilocalorie per mole. Cool. Another thing, we can also break bonds by performing torsion of them. And a good example is ethylene again, but now a torsional scan. So we can break the pi bond by performing this torsional scan here. And same thing happens. You have an instability region when you are breaking this bond, and you are going from unrestricted to unrestricted calculation. So that's also something. What's the barrier for this torsion? And here I show the results. And in this case, I tried to perform stability also with coupled cluster results. So we can look here that omega B97XT with DF2 SVP with a stability analysis predicted a pretty good torsional barrier compared to the reference value of 60 kilocalorie per mole, reference value grabbed from this paper. If you only use coupled cluster, like no stability analysis performed, you see that you have this kind of peak here. But when you use stability analysis, you fix that. You don't have the best torsional barrier compared to the reference value, but you fix the peak if you try to use that. This is something that I want to look more into, how this stability works for ab initio methods like coupled cluster, but we'll see. And then here, I love densities. As you can see, I'm always showing orbitals and densities. You can see what happens to the orbitals when you are performing this torsion, and then you can see here the pi bond being broken. So you can see exactly the moment that this happens, which, in my opinion, is fun. These are my favorite movies for a Friday night, but in this case, Friday morning, right? Okay. So to wrap up everything, summary, with Julia, we can post-process electronic structure calculations from existing software, ORCA, for example, calculate electronic Hessian with respect to orbital rotations, detect and fix instability of wave functions. Conclusions, we can use stability analysis to optimize geometries, to break bonds by torsion and by stretching, and future work, expand documentation and stability analysis to evaluate complex instabilities. That's my next step. And then I would like to thank my chemistry department, my advisor, Professor Tomasz Kowalewski, my committee members, PSC for supporting my work with Julia, NSF, and thank you all for your attention.
Thank you. We have time for one quick question. Anyone?
Thank you for the nice talk. I was wondering, can you also get unlucky and land in a local minimum? and then your stability analysis says you're fine, but actually you want to be somewhere else?
Oh, okay. So you're asking about when a stability analysis doesn't work and kind of deceive you, right? And tells you you're. So this can happen. I will tell you a case, dichromium. I don't know if you ever tried to break dichromium. Stability analysis is not working for that, and I'm trying to elucidate why. So with d orbitals, you have much more degeneracy, so it becomes more and more complicated, right? So yeah, that's one case. And then I'm trying to figure out exactly why. I suppose there may be some complex instability with d orbitals, because we suppose they are real, but they shouldn't be, right? In real, they are actually not real. So that's what I think is happening, but I need to investigate more. Okay? Just one quick announcement. So we are in the computational chemistry mini. I know most of you know who John Popple was. John Popple was a chemistry professor here at CMU, and he won the Nobel Prize in 1998. And if you go to Hunt's library at CMU, you can actually take a picture with his Nobel Prize medal. So that's a great suggestion. You are visiting Pittsburgh. If you want to go there and take your picture with Popple's medal, I
That's
recommend.
Awesome. Please do. Please give Leticia another round of applause for the beautiful talk. So our next speaker is Shuhei Ohno from Yokohama City University, also affiliated with JuliaCon from Japan. And he will tell us about quantum mechanical two-body problems in Julia. Again, I will remind you when there's 2 minutes left for the entire talk.
Okay.
And please take it away. Thank you.
Thank you. Thank you. Hello, I'm Shuhei Ono from Japan. This is my GitHub account, and please scan this QR code, and please follow me. And if this is very cute QR code for GitHub repositories, GitHub projects. You can use it with okay. Anyway, yeah, you can use this QR code generator for the GitHub project. And we are from Japan. Sorry, you are scanning. We are from Japan, yeah. There was many kinds of accidents, the delay and cancel and package lost. But yeah, this is the second exciting thing to me. But the most exciting thing is this event, JuliaCon. I'm very happy to come in here. In Japan, we hold Julia workshop. We held Julia workshop last December, and the participants is 30 on site and 150 from online. And yeah, this is the photos, and here is statistics. There are 80 students and near 80 researchers. And here is another graph. When you started Julia, yeah, there are many. There are 60 new users. So we are getting new friends by holding workshop in Japan. So please come to Japan. So yeah, here is Valentin. Yeah, we invited him. So please come to Japan, and we will hold a seminar for each of you. And this is a book of Japan. Books in Japanese. There are 10 Japanese books about Julia. And there are about 2,000 articles on Kita and Zen. This is a platform of the technology information's website. And Satoshi Terasaki is a second contributor in the Japan Julia community, and I'm the 8th contributor. And then this is the last information about the Japan community. Yeah, some people read my articles from US and Taiwan and China and European countries. And Tokyo is the biggest place, have biggest population, so there are most population of Julian. But at Osaka and Kyoto, yeah, they are famous university, Osaka University and Kyoto University. And Fukuoka also have Kyushu University, and here is the Tohoku University. So there are many users for each high-level university in Japan. So this is a state of Julia in Japan. And today I would like to talk about Julia for full-body systems physics. What is full-body systems physics? As you know, proton is made from up quark and down quark. This is three-body system. And there are 1, 2, 3 kinetic terms and 1, 2, 3 interactions. And the proton and the electron is called hydrogen atom. This is a two-body system. Yeah, proton have 3 quarks, but in this model, we consider proton is 1 particle in our model. So there are only 2 kinetic terms and 1 interaction. And also this is most famous, most popular example of three-body systems. This is a proton and a deuteron and electron, and there are Coulomb interactions. So this is the example of full-body systems. Full-body systems physics. Full-body systems has very simple Hamiltonian. So full-body systems physics is very good law as a trading port of calculation methods. Yeah. We import the method and we export another method to another field and provide the benchmarks. For example, my main topic is quantum chemistry, but my method is coming from hypernuclear physics via the full-body systems physics. But there is no open source package in full-body systems physics, so we want to develop good packages. And we launched the Julia full-body. This is a new group to develop full-body packages for full-body systems physics. Yeah, please visit this group and please follow our project. Our goal is a full-body JL, a package for quantum mechanical full-body problems that is open source and open formula, open derivation, and any particle, any number of particles, and any interaction, and several methods, Rayleigh method and Monte Carlo method, and DFT or any other method. So for this project, we developed 2 packages, many packages. And at first, I developed Antique JL. This is a package for testing two-body JL. And the two-body JL is a prototyping of full-body JL, our goal. So today, I would like to introduce this package, two-body JL. We published this package last November. Yeah, please visit this QR code and give me a star. This package has currently two methods to solve full-body systems physics. Oh, thank you for scanning. The reason why I developed this package, yeah, please try a calculation. please derive this matrix element. This is the most easy example. This is overlap matrix of basis functions, between basis functions. Yeah, it's really, it's most simple one, but it's hard. And there are harder calculations. So we should write this derivation to the documentation as a doc string. So please write the formula and the step-by-step derivation. Yeah, this is a most important point, most important message from us. And this is a usage. Install this one. And here is a code to calculate the hydrogen atom, variational calculation of hydrogen atom. This is Hamiltonian, and this is the code of Hamiltonian. There are two terms, and there are 2 lines. And there are 4 basis functions, and there are 4 lines to define the basis functions. This is almost same as the formula. And please input the H Hamiltonian and the basis set to solver. And we get the basis function and linear coefficient of the linear combination. This is a wave function and the norm and eigenvalues. So this is the ground state energy of hydrogen atom. Yeah, this is very nice value to the for only 4 basis functions. And this is introduction to this package. And this two-body systems is very too simple in quantum chemistry. There is only one hydrogen atom. But in hadron physics, there are interesting examples. This is lambda C. This model is a 3-body system, but in the efficient model, we consider it as a 2-body system. And this one is a charmonium. This is a 2-body system of charm and anti-charm quark. So we can calculate the mass of these systems. So this package is not just a prototype. We can use this one to research in hadron physics. This is a paper we published about heavy quark, heavy mesons. This is the outline of calculation. This is the Hamiltonian, the semi-relativistic kinetic energies, and the potential linear constant term and the linear term and the Coulomb-like term and the hyperfine interaction. And we must calculate the matrix elements to convert to the linear matrix eigenvalue problem. And we can solve this matrix eigenvalue problem by using linear algebra, JL. But we must optimize the nonlinear parameters. So we used OptimJL. And here is my work to calculate the accurate mass and eigenvalues. We are generalizing this work. In the 3-body and 4-body, more body systems, it's very hard to calculate matrix elements and use Gaussian basis method. So we developed the Metropolis algorithm, .jl, to use a variational Monte Carlo method in 3-body systems. And the variational Monte Carlo method is good at using machine learning. This is our next step, and there is another problem about coordinate systems. In 3-body systems physics, we use Jacobi coordinate systems, not Jacobian. But some some papers say it's Jacobian coordinates, but this is not correct. And the Jacobi coordinate system have three ways in three-body systems. But 16 ways. There are 16 ways in four-body systems. And 120 ways in five-body systems. We must calculate of the transformation matrix for all of these coordinate systems. So it's very hard by hand, so this package is necessary to generalize any number of particles. And yeah, this is an example of six-body systems. There are 720 ways of Jacobi coordinate systems. So we are developing this package for generalized number of particles in the few body calculations. That's all. Thank you for listening.
All right, we have about 10 minutes for questions, but I would like to thank Shuhei for making all the way from Japan to here, and I heard some troubles he encountered earlier getting here. But yeah, please, any questions?
Thank you for the wonderful talk.
Thank you.
My question is about dissociated systems. So does your two-body system or the Hamiltonian allow the particles to completely dissociate? And how do you treat separated systems?
Separated systems? So what?
So dissociation. So if
Dissociation of...
in case of hydrogen atom, that will be ionization.
Yeah. I see. That system is currently this package is not cannot calculate this dissociation because this package doesn't have the complex scaling method. If we implement the complex scaling method, we can calculate the dissociation of the molecule or other systems. But currently there is only one only for bound state system. So I will implement another method, or please contribute to this package. Thank you.
Do we have any other questions?
Could you expand a little bit more on the Jacobi coordinate system, and I guess what kind of physical systems that be applied to?
About Jacobi coordinate system?
Yeah.
In the few body calculation, we must eliminate the center of mass motion. But there are another choice of the coordinate systems. But the Jacobi coordinate systems can make the Hamiltonian simple Hamiltonian. There are only only Laplacian terms of each particles. But if you use another coordinate, there is a product of Nabla operators of each particle. So the good point is, and that is a good point of Jacobi coordinate system.
Thank you.
Any other questions?
Cool. I have a related question. I was wondering, how does the number of Jacobi coordinates scale as the number of particles increases?
Jacobi coordinate system. Number of Jacobi coordinate systems is increasing. Increase depends on the particle exponentially. So we cannot use all of the coordinates. And so we must choose which type of systems, coordinates, is the best. So, but there is no package of Jacobi coordinate systems. No one knows which patterns, which type of coordinate systems is good. So we must research about Jacobi coordinate systems.
We'll have to screen through them
Yeah.
to choose the best. That's good.
So, yes, no one has the clear answer to that.
I have a few questions. So, you said the two-body problem is not challenging enough for you.
Yeah.
But you can keep on adding complexity into your Hamiltonian. You show trapping potentials, but you can add spin or recoupling, and you can add other kinds of, say, trapping potential, the external field. Say probably not much, but probably a lot is going on to form the so-called ultra-cold molecules. So they're moving on from ultra-cold atoms. Do you think you can extend your package?
Yes, the one developer is coming from cold atom physics. So we will support the external potential, like a harmonic oscillator trap or any other trap.
So what do you think? How about go even a step further? Instead of like just having point particles, can you have like point, say, vortices? Then the two vortices interact through some kind of different potentials, and then with boundary conditions. Have you thought about that?
So
vortices, like pseudo particles or some collective behaviors with the two, say, blobs rather than just two particles. Is there any interest for you to kind of go to that direction?
Sorry, I couldn't catch the question.
Vortices. They are, the sense like you spin the water, you get the funnels, and they can be kind of pinned with some kind of potential, and then you have two that interacting. So it's more complicated than two particles, but they're still two-body.
If you can define the potential, we can calculate by using this package. But so the problem is that how to get the formula of potential. If possible, we can calculate.
Yeah, another smaller comment I want to mention is I found this package is potentially very, very useful for educational pedagogical purpose. This can be like very good tools to teach like undergraduate graduate level field body physics or theoretical chemistries. And these are you build things from ground up at the beginning, since they're accessible for the students to try run the code to modify the algorithm to even just understand the interactions behind the scene. I find them really, really beautiful. So thank you.
Thank you.
Do we have any other questions or comments? We still have quite a few.
Have you tried or experimented with combining like Jacobi coordinate systems with like something like a floating Gaussian basis set? With like using Gaussian basis sets along with the Jacobi coordinate system.
Many researchers are trying to use Gaussian-based functions for field-body system physics, but limit is 5 or 6 for these systems because the matrix size is too large.
It would be really cool to actually combine a quick box with this package, I think. But we can talk later.
If no further questions, let's thank the speaker again.
Thank you.
a few minutes slightly ahead of the schedule, so it's time to take a few minutes break. We'll restart at 11 sharp. Yeah.
Good.
Yeah. Good morning, everyone. Thank you for coming to the Computational Chemistry and Material Science mini symposium at JuliaCon. And the next speaker is Lucas Weber from Center for Computational Quantum Physics, Flatiron Institute, New York City, talking about Carlo.gl, high performance Monte Carlo simulations in Julia. Please, floor is yours, Lucas.
Hello, everyone. I'm Lucas. Today I want to talk to you about this little package, Carlo.jl, which is a framework for high-performance Monte Carlo computations in Julia. First of all, let's start with the question: what is Monte Carlo? In Monte Carlo, the idea is that you want to solve a high-dimensional sum or integral by using random numbers. So imagine you have a function f that you're integrating over, and then if you can write that function as a product of another function g times a probability distribution p, then you can reinterpret this problem as a sampling problem, sample from this probability distribution, do the statistical average, and solve your integral that way. In practice, the way we sample these probability distributions is using a Markov chain. So we pick some starting point x, and then we keep doing random updates in a certain way that converges to the target distribution after some time. And if we do this for long enough, we get this Monte Carlo time series, which is autocorrelated, but if you do a time average, you arrive at something that converges to the correct result for the integral. The statistical uncertainty of this average is then scaled then as 1 over square root of the number of samples, which in low dimensions is pretty bad, so please never do this for 1D integral. But in high dimensions, this doesn't actually depend on the dimension, so it becomes a really powerful method. And this is exactly what makes Monte Carlo, or what we call quantum Monte Carlo methods, so popular in condensed matter physics, where we're interested in sampling objects like the quantum partition function or the many-body wave function. The slight problem here, however, is that these objects, either they don't have a straightforward interpretation in terms of a probability distribution, or that interpretation is just very hard to evaluate. You cannot calculate the weights of the distribution. So what you need to do first is you need to find a mapping which might not always exist, and if it exists, it depends on the system. And this mapping then maps your complicated quantum object into a classical probability distribution, which can be can either be a discrete or continuous or both. And this probability distribution then lives typically in a very large configuration space that's even larger than the Hilbert space that you started with. But high dimensions in Monte Carlo is not such a big issue, as we learned, so we can just eat this, and as long as we can sample this distribution, we can use it to understand our system. Sampling this then requires another set of system-specific tools that we can use, and then we carry all of this out, and out comes a whole lot of data, so order of terabytes it can be. And this data you take, do statistical post-processing, extract averages and expectation and error bars for your quantities of interest, and then you're done. So if you look at this whole program, you can divide it into two parts. One is the system-specific part, which I call the fun science, where really you drive the field forward by innovating new methods and trying to optimize your algorithm. And the rest is basically the bookkeeping that always stays the same. But since these problems tend to be such large-scale problems, you really want to do this in parallel. You want to do the sampling in parallel, and if possible, it's also nice to have a workflow that prevents errors and maybe is understandable to another person as well. And the desire to have all of this at once sort of is the reason for Carlo to exist. So Carlo is a framework that allows you to write these kind of simulations, and it takes care of the bookkeeping for you. So you get a Monte Carlo-aware MPI scheduling of your sampling. So you can give it a number of machines, and they will collect samples in parallel across different parameter sets, you name it. And the second thing it does, it takes care of your input and output files and provides a checkpointing facility. So if something goes terribly wrong, you run overtime with your very long simulation, it's fine. You can just restart it from the point where you left off without losing much progress. And then what it does is binning analysis and jackknifing, which are the techniques that we use for the statistical processing to get our results from the sampling. And for Monte Carlo experts, the idea is that they can focus on the fun part, quickly develop a new method, and then get all of these bookkeeping things for free to get basically a production-ready code out of it. And the hope for non-expert users is that, okay, if we provide this unified interface, this makes existing codes easier to use and makes Monte Carlo methods more accessible to the general public, maybe. And these two viewpoints are exactly what I want to structure the rest of the talk about. So I'll showcase first, in the first part, how to implement a simulation code. We're going to do a very simple model. And then in the second part, I put on my user hat and I show you how to run a pre-existing code that is built on Carlo. So starting with the first part, what we're going to implement is a simulation of the Ising model. So imagine we have a magnet that lives on a square lattice, and on each of the sides there's a spin that can either point up or down, which is modeled by this variable sigma, which can be either +1 or -1. The interactions of the model are then along the nearest neighbor bonds of the lattice, and the distribution we're interested in is the Boltzmann distribution of the system. And to simulate this model using Monte Carlo, there's 3 basic things we need to do. First, we need to choose some initial spin configuration. Then we need to implement the Monte Carlo update, which takes us from one configuration to the next in a way that fulfills detailed balance and converts us to the Boltzmann distribution. And then we need to implement observables like the magnetization that can teach us something about the state of the system. Implementing these things in Carlo works by implementing this abstract Monte Carlo interface, which we just subtype here. And for the Ising model, what we need to store is just the temperature of the system and a matrix that stores the Monte Carlo configuration, all the spin states on the lattice, which we just do a matrix of integers here. And then all the rest is implementing methods that act on this type somehow. Starting with the construction and initialization. So first thing we need to realize here is there's actually 2 kinds of initialization. The first one is the constructor, which is called each time a simulation is started or restarted from a checkpoint. So the task here is just to set the parameters and set up our data structures, but not doing anything physical or setting up any spin configurations. So that's what we do here. The parameters, there's this a dictionary we get passed as an argument, contains input parameters that come in from an input file that we will see later. So here we get the system size and the temperature, and then we allocate a matrix. Then the second function, this carlo.init, is the one that's really only called when the simulation is started, and there's where we set our spins to some random numbers. One little detail here is, additionally, we get this Carlo Monte Carlo context pass, this CTX. And whenever we want to use a random number in Carlo, we should use this ctx.rng, and by doing this, our results become reproducible. We can set a seed in the config file, and then everything stays the same. So that's the initialization. The next part is the heart of the algorithm, basically. It's the Monte Carlo update. And for the Ising model, there's a bunch of different choices you could have. We just take one of the simplest ones, which is the Metropolis update. And that works like this. We just choose one side at random, and then we flip it with a probability that's related to the energy difference such a spin flip would cause. And then the Carlo function we need to implement for this is carlo.sweep, and sweep is basically a Monte Carlo jargon for do enough updates so that you significantly change the configuration. So we implement, we repeat this Metropolis update for as many times as there's number of spins in the lattice. And you see here, choose a random site, calculate the energy difference, and if we have to, we flip the spin. That's the sampling done, okay. And now measuring observables works, we focus just on the magnetization and the spin-spin correlation function here to keep it simple. There's this function carlo.measure, where you do the measurements, of your observables, and for the magnetization, we just do the average of the spins over the lattice and the correlation function. You could do many fancy things using symmetries here, but the simplest way is just look at the correlation function in the x direction and average over the y direction. And lastly, we need to take these things we calculated and call this function measure on the context, and that will save one sample in the time series, basically. So we were interested in the second and fourth moment of the magnetization, and for the spin correlation. One note here: these observables, they can be either scalars like the magnetization moments here, but they can also be vectors or arbitrary shaped arrays like the correlation function. So this is the main thing, and now there's some features that may be not so obvious. So if we have these averages, sometimes we're interested in nonlinear combinations of them. Take, for example, this Binder ratio here, which is defined as a ratio of moments of the magnetization, so m squared divided by m to the fourth. And this guy, our basic statistics tells us if we just plug in the averages in this nonlinear function and there's some error bars, we get a bias, right? And this bias can be pretty significant because imagine you have some disordered magnet, then this distribution of the magnetization moment can be actually squeezed against zero and quite non-Gaussian. So it's important that we have something to correct any biases and also get the correct error bar. But yeah, Carlo has your back on this. There's this facility called evaluables. You have this register evaluable function where you can define functions of the observables and Carlo will do jackknifing and correct the bias and give you the correct error bars for this one. Now there's only one last thing, I promise. For the checkpointing, Carlo uses HDF5, so it expects you to implement these two functions. Write checkpoint and read checkpoint, I just save and read the Monte Carlo configuration from an HDF5 group. This is, for just a spin array, it's a simple thing. And then we're done, our simulation is implemented. And now the reward for going through this implementation part of the talk is we get to run some simulations now. Let's start with the easing code that we just implemented. So the way Carlo is structured is it's meant to be used with MPI. So the whole recommended workflow is to write a job script that you can then later run with MPI run. And that works like this. You start by importing Carlo and Carlo job tools, and then this easing code, imagine everything we just wrote is in a module called easing. Import that as well. And then we want to set the parameters of a simulation. And we want to set not only just one simulation, but a bunch of simulations that Carlo then can parallelly schedule with work sharing and so on. And the way to do this is using this task maker tool that's defined in the job tools. And the task maker, each property of the task maker is a parameter in the simulation. So we start with these three properties, sweeps, thermalization, and bin size. They are Carlo internal, and they're the same for every code that's built on Carlo. The sweeps are just the number of updates you want to do in your simulation. The thermalization is the updates you want to do at the beginning of the simulation without taking any measurements, because remember, these Monte Carlo Markov chains, they need some time to thermalize to get to the right target distribution. And then the last thing here, bin size, that is how many samples of your observables are averaged before you write to disk. This is a pure memory and bandwidth saving feature, not related to the statistical post-processing that happens after the simulation, which also does binning. So you can choose whatever you want here, the results will be the same. You just should choose so many that your disk isn't full, and so not too many, so that you still have some bins left on your disk that you can do the post-processing on. And then we set the system parameters. So our goal here is to do simulations for a bunch of different lattice sizes and also a bunch of different temperatures. And the way this works with the task maker is that each time you call this function task, it creates one snapshot of all of its parameters that you've set. So we call this, we go through this loop, we set the temperature and the system size at each iteration and then call task. Yeah, I found this way of programming your job file or your parameter sets pretty handy, especially in the case where you have something more complicated that nested loops. Like if you have a very let's say you have another thing that gives you a data frame of certain parameters, you want to get them, you want to pre-process, filter them before you put them into your job file, then you can program all of that and make your parameter set that way. Now let's say we are done with that, and then we put everything in this job info structure. Yeah, the first argument is the job name or the directory where we want to save all the simulation data at. The second parameter is the type of the subtype of abstract MC that we implemented in the first part of the talk. Then the runtime is the maximum time the simulation will run for. So if you set a large number of sweeps and you cannot finish within the runtime, it will just go until the runtime and then say, okay, I give up, I save everything, I save a checkpoint, you can restart me with more runtime later. The checkpoint time is the time interval between saving checkpoints. And then the tasks is the number of parameter sets. So if you don't like the task maker, so make tasks takes the task maker and spits out an array of task info objects. If you don't like the task maker, you can also build the array in your own way and put it in there. And then start is what starts a command line interface that you can then use from your console. So that's the job script. Let's run it. And yeah, I run it with MPI run or srun on your cluster. And with a given number of cores, Julia, then the example job.jl, where we wrote this stuff from the last slide, and then the argument starts the simulation. There's also a bunch of other features in the CLI which you can explore with --help. For example, you have a feature like status that shows you the status of an ongoing simulation. Or my favorite feature for impatient people, you can collect data that's already there from incomplete simulation. So if you're impatient, you can just check what's already there and test if your post-processing pipeline is working and stuff like that. But let's just assume we're all patient here and we waited until this is over. And then our results got saved. And then Carlo has a little tool that allows you to extract the data that it spits out, which is all of the statistically post-processed results are in the JSON file that is called like this. And then you call this data frame method here, and you get a data frame. The columns of this data frame are all of the parameters of your job and also all of the observables and these evaluables from that we defined. For example, here the binder ratio, and then I can plot them, and I see something like this. Yeah, remember the binder ratio was this strange ratio of magnetization moments, m² divided by m to the fourth. Here is a function of temperature. And the binder ratio is defined in such a way that it has a crossing at different system sizes when there's a critical point. So we see here for the Ising model at around 2.269 or something, we expect the critical temperature, and that pretty much fits with this crossing that we see in the curves. Yeah, so that's great. But of course, I don't want to let you out of here with just the Ising model. There's a little extra treat. We're also going to look at stochastic series expansion JL, which is a state-of-the-art quantum Monte Carlo code for spin system that's built on Carlo and available for you right now. It has a lot of knobs where you can generalize it to a lot of different systems, but one thing that's implemented out of the box is this anisotropic Heisenberg model with this Hamiltonian. And since we're in the chemistry and materials section, I feel obliged that we should calculate something for actual material. So there's this anisotropic honeycomb magnet, barium nickel vanadate. It's a spin 1 magnet, and there's a simplified Heisenberg model description of it, where you just take the nearest neighbor honeycomb exchange coupling, and this single ion anisotropy and the easy plane single ion anisotropy term, DZ. Set them to those values, and then let's put it in a job script. It's a bit more complicated for the Ising than for the Ising model, because this code has a lot of more features. So we say we want to have this magnetic Hamiltonian that we saw. This the magnet model. Set spin equal 1. It also supports arbitrary spin on arbitrary lattice size, but let's skip that for now. The lattice should be a honeycomb lattice, and the size is 40 by 40 unit cells, which actually you need in this case because the model has some long-range magnetic correlations at low temperatures. Then the exchange coupling and the anisotropy from the paper. One thing for numerics, I think, is always good to work in the natural units of the problem. Also, I see as a typo that should, no, it's not a typo. I rescaled everything in terms of units of the exchange coupling, but that's okay. And then we want to simulate a bunch of different temperatures, so I do just this one loop about temperature here. Put it all into the job info and start. This, with a 40 by 40, it takes a bit longer to run. But once you have that, you can compare it to the experimental data, which is the black curve, and then the blue is a QMC plus a constant, which is a diamagnetic contribution that's not captured by this Heisenberg model. And you see it fits rather well, except for low temperatures. And this low temperatures, probably there's some other, the simplified model is not quite enough. Probably there's some next nearest neighbor exchange couplings or something else that becomes important. But I think it's a handy tool in case you're an experimentalist and you like to check the model parameters you got from some other place. You can try to use this code. And with this, I'd like to conclude. Carlo JL and Stochastic Series Expansion JL are available for you as registered packages. There is documentation which describes a few more advanced features like non-trivial parallelism. So far we've only seen the trivial, embarrassing parallelism of Monte Carlo simulations. You can always collect in parallel, right? But Carlo also lets you define parallelism within the sweeps and measurements themselves, if you want that. There's a parallel temporal feature, and for stochastic series expansion, all these ways to expand the Hamiltonian that you want to study. And then there's, apart from the documentation, there's the Cyphos physics code basis, which is available and has some explanations on the inner workings and benchmarks. And if any of this made you curious and you want to, or you're building something with it, you can always let me know. And if you run into issues, I'm happy to help. Thank you for your attention.
We have time for a few questions.
Hi, thanks for the nice overview. So I'm wondering how I should think about this sweep step. Can I also think of it as just a single step in my Markov chain? So here you said that you had to take an efficient number of steps or sufficient number of steps, but I guess that was just your model. But if I have a model where I don't like to do that, that's also fine.
Yeah, this reminds me a little bit of the keynote this morning. When I wrote this code, I was following the jargon of my field, where the sweep is like some way to just say update. So if I had written it again, probably I would just call it update. But basically, think of it as the update in your the step in your Markov chain. It doesn't really matter as long as it's. The reason I repeat the spin there is because if I want to scale up my system, I repeat the Metropolis update is if I want to scale up my system, I want the update not to be less efficient with increasing system size, right? So you can just put whatever you want, basically.
Okay, thanks.
Yeah. Yeah.
Apologies if I missed this during at some point during your presentation, but are you running multiple Markov chains per thread? Because one reason I mentioned this is because with how Julia's base rand call works, if you are using that, it goes faster if you are calling multiple, if you're asking for multiple values at a time. Because it can pull, I believe, 8 in parallel for floats, I think. And you could see maybe, I think, around a 4 times speed up, I think, if you're doing 8 chains at a time on each thread.
So in this case, the parallelization is MPI, so only one thread. But yeah. So if I have only one thread, I should get random numbers in parallel, you're saying?
Yeah, I think you could, basically instead of getting one random number at a time, you could be getting maybe 8 at a time, and I think you would see a speed up.
I see.
Yeah.
So yeah, I hadn't thought about that, but the thing is, usually, so for these things, often the random number generation isn't actually the bottleneck. You're either doing some linear algebra that's also pretty expensive on the side, or you're jumping around a big array and have some memory bottleneck. But it's
true.
Interesting to think about in the cases of random numbers. Yeah.
Any more questions?
I have a quick question. You store your spins in a matrix of 8-bit integers.
Yes.
But can they just be stored in the single integer that 0 is spin up and 1 is spin down, and that will shrink your memory usage by quite a bit?
Yeah, you can optimize this quite a bit further. Just for the sake of the presentation, I went with the simplest way.
All right, let's thank the speaker again.
Yeah.
Our next speaker is Hainan Wang from University of Pennsylvania, talking about Elastic Networks.jl package for metamaterial research and design. Please take it away.
Yeah, thank you, Ray, for the introduction. I'm Hainan. I'm a postdoc at University of Pennsylvania. And today I'm going to talk about this package on Elastic Networks. So a little bit about myself. I'm now a postdoctoral fellow at this very vibrant community called Center for Software and Living Matter at Penn. So, on the top is a photo of all the postdoctoral fellows. And last year I graduated from Princeton. My thesis worked on statistical mechanics, chemical physics, and metamaterials design. And now at Penn, I'm more gearing towards biophysics and biodynamic simulations. I've been coding in Julia since 2021, and I love Monte Carlo simulations, as I have talked about, and also molecular dynamics, and I love Optim.jl and all the geometric packages. Yeah, so today I want to talk about metamaterials. So these are materials that doesn't really worry about the grabbing and giving away of electrons, because they are on a more mesoscale or macroscale level of matter. So these are actually natural or engineered materials whose properties really arise from meso or macroscale structure, not just the chemical composition on the molecular or atomic level. So some examples include this 3D printed structure, knitted fabrics. It doesn't matter which yarn we are using, as long as it's the right sequence of knit and purl stitches, you have the similar elasticity behavior of your sweater. And some other examples include hydrogels. So these are biopolymer filaments that are like stapled together by these green crosslinks. And also origami and kirigami, it doesn't matter on which paper we are folding them. It's the way that we fold them that's important. So actually, in biology, we have a lot of metamaterials. So cells and bacteria have found these metamaterials again and again. So one of the cool examples is the actin cortex. So when we have a cell, and on the inner layer that underlies the cell membrane, we have this actin cortex that's made of actin filaments. It's a protein that is really long, and it lies just beneath the cell membrane. So if the cell doesn't have the actin cortex, it will be just a bunch of water and lipids that's really soft. So it cannot support our bodies. And so yeah, this cortex supports the cell shape and regulates all of its mechanical responses, like division and motility. And also on the outer side of the cell membrane, we have this collagen network on the left-hand side in the extracellular matrix that binds cells together to form a tissue. So if you look at the scanning electron microscope, these are also elastic networks. That is a metamaterial. And as another non-mechanical example, we have in the feather of birds, because birds cannot use heavy metals to create the color blue or green, so it has to use structural color. And these structural colors are made of beta-carotene nanoparticles that create air channels in the feather, resulting in diffraction of light that can show blue or green. Yeah. So it turns out that many of these mechanical metamaterials, though not including the birds, that's optical, but for the actin cortex and the collagen network, those can be modeled as elastic networks. And also macroscopically, a knitted fabric is an elastic network. So here, for example, for the actin cortex, the filaments can be modeled as elastic springs, and the cross-linkers that bind the filament together can be modeled as nodes that connect the springs. And for the knitted sweater, of course, the entanglement of yarns is a node, and the yarn between two nodes is a spring. So elastic networks, as I have said, has been rediscovered again and again in biology and civilizations alike. So in the UK and in China, we have different words for knit and purl stitches, but these have been developed independently. I thought this is because elastic networks are very great materials if you think about material economy. We only use a little bit of matter that form these springs to create matter that can withstand load and that can be stiff. And another cool thing about them is that they are highly programmable down to the individual edges and nodes. So a spring can appear and disappear, a cross-linker can bind and unbind. And these are really tuned by a lot of enzymes in our cells. And of course, if you are a knitter, you can really program what is your next stage. So as my advisor, Andrea Liu, always say, many more is more different. This principle happens in neural networks where we tune the weights on each node, on each edge of our neural network, and they also happen in these mechanical networks. So we are just beginning to appreciate how metamaterials are going to have a lot of learning capacities and adaptations in both engineering and biology. And then I thought, okay, as a Julia community member, we really need a general infrastructure to build and test these elastic networks. And I'm not the first one to think about elasticity in Julia. So if you want to experiment with continuum elastic materials, so not networks, but a continuous body, then you can go to JuliaSFEM. Yeah, but my approach is more agent-based model level. So I want to look at each edge and each node to understand their programmability. Cool. So yeah, here's an advertisement for elasticnetwork.jl. Of course, this is still in a prototypical version. I just released 1.1.0. But I hope that in the long run, this will be a go-to platform to design, model, and test metamaterials based on elastic networks. So yeah, currently in this version, we have these kind of features. We can customize the topology that is compatible with graphs.jl. I love that package. And the star function of this package is it uses automatic differentiation to extract exact linear response stiffness tensor. So no finite element method, that's automatic differentiation. And I support periodic boundary conditions with deformable unit cells. The unit cell is our simulation box, and you can really twist and share this simulation box to create a lot of different deformation modes on our material. And we have topological tools that allows you to add and delete edges, split and merge nodes. And we have, of course, visualization with Mickey and input and output with JLD2. Yeah. Cool. So yeah, here's a quick start. But what we can do with this package is you can really test how does topology affect the elasticity of our elastic networks. If you are doing 3D printing with the rubber bands, for example, you can prototype it on this package first and iterate on the topology to understand how we should design this elastic material. So as a quick start, it's on GitHub. You can create a diamond network that has 1,000 nodes. And for the simulation box, we have side length equals to 10, and it's a cubic box. And this 0.05 means the pre-string on each edge. So as the box and the elastic network has been created, the length of the edges is already 5% larger than the rest length. So this is needed to maintain rigidity for a low coordinated network. Now, we don't need that if we have a cubic network that has 6 edges per node. But because diamond has only 4 edges per node, we need this pre-string to maintain shear rigidity. Okay, so I will show the result on the next slide. But first, let's delve into what does a network struct or object contains. So firstly, it contains a G that is a graph specifying which node is connected to which node. It uses graphs.jl. Secondly, it has a basis that tells us the basis of our simulation box. So it can be a cubic box, but it can also be any parallelepiped. And we can change them. And thirdly, we have points that specifies the coordinates of nodes in space. And it's relative to the basis. And then we have 3 properties for each edge. So of course, we have the rest length of the springs. We assume that they are harmonic springs. And we have stiffness modulus, or Young's modulus, for each edge. That's the last point. But then we also have this interesting image info, because we are in periodic boundary conditions. And this image info tells us which of the image of node J is connected to node I. So if I have node I and node J in the same image of the box, then image info is 0, 0, 0. But if node I is connected to node J in the neighboring box in the x direction, then the image info will become 1, 0, 0. So you can really create an edge that goes wraps around the box. Okay, so here are the results for our demo that's on GitHub for the quick start. So we have a box side length equals to 10, pre-string equals to 0.05, and we can visualize a network on Makey. So you want to install GL Makey if you want to drag around the box. Yeah. So because I need to do CI, I upload on the uploaded version is Carol Makey. Okay, so here is a diamond network. And we can now do something cool to the network. We can edit its topology. So first, let's look at which edges this network contains. So we do collect of the edges of the graph associated with the diamond network. And it shows us all the edges, for example, edge 1 to 501, from node 1 to 501. But these are not non-directed edges, so it can also be 501 to 1. Yeah. Then we can say we remove edge from the edge from node 1 to 501. And then we relax the network, we minimize the energy, and we can visualize the network again. So it's on the right-hand side. So as you can see, because we have removed an edge close to the origin, there are many edges, a few edges around the origin that also become tensionless. So tensionless edges are shown by white color. But there are also other edges away from the pruned edge that are getting more tense, so the color becomes darker. We can really play with the topology, can merge nodes and split nodes to see how the tension distribution has changed according to the edits. And of course, another thing that we can do is we can compute the hashing of the elastic networks. And when we diagonalize the hashing and compute their eigenfunctions, they become the vibrational modes. So we can do that, and we can visualize the vibrational modes. So if you are familiar with molecules, we know that a water molecule does this and does that. They have vibrational modes, and these are the same. So an elastic network has their own vibrational modes. And of course, that depends on the periodic boundary conditions or other boundary conditions. So here we have a lot of edges that are moving to the right-hand side. And on the opposite side of the box, there are some nodes that move to the left-hand side. Cool. So that's what you can do. And the star function of this package is to compute the linear response of the networks with infinitesimal string theory. So actually, when I submitted the proposal for this package, this is the only function. And then it has grown to a full package. Yeah. So a little bit about infinitesimal string theory. So this has been around since the time of Cauchy, so more than 200 years. And strain is the deformation to the material. And stress is the force per area as the result of the strain. So that can also be the first derivative of the electric energy per volume to the strain. So assuming the strain is infinitesimal. And then elastic modulus is stress over strain. So that's a generalized Hooke's law. And it can also be second derivative of the elastic energy per volume to the strain. And then my colleague Marco has found out how to compute the stiffness tensor with a finite amount of strain. So we can, for elastic network. So we can imagine that we, for example, stretch or share our simulation box, and then the nodes in the box will, of course, respond to that stretch or share. And for example, if your node is originally at the center of the box, after your share, you may think that okay, after the share, that node is still at the center of the box. But that's not exactly true, because when you share by a finite amount, then there's a little bit force on that node already, because all the springs get stretched or compressed. So we want to know what is the force on each node, and we want to compute the non-affine displacement on those nodes. So non-affine means it doesn't really correspond to how the entire box has been deformed. There's another correction to that. So for a finite but small strain, this equation A4 is approximate, because you really have to minimize the energy after the finite strain. And this is just one step of the Newton-Raphson energy minimization. But then I thought, okay, if I have an infinitesimal strain, then this A4 will become exact. And how do we treat infinitesimal string theory? We use automatic differentiation. That makes A4 exact. So this is the cool function that computes the moduli. So here in the first block, there are different ways to poke our box infinitesimally because we want to know all the components of the stiffness tensor. And then we compute Hessian around here. There's an H. Yeah, that is our Hessian. By the way, because our edges are harmonic, the Hessian is analytical. So it can be computed in less than a microsecond for 1,000 nodes. And then we minimize the energy under the deformed basis. But because our deformed basis is deformed infinitesimally, so this so one step of Newton-Raphson suffices to calculate the infinitesimal non-affine displacement of the nodes. And then we minimize the energy under the deformed basis, and we can compute, we call a forward diff Hessian to compute the component of the stiffness tensor. And after that, we can compute the bulk and shear modulus by adding up all the components in the stiffness tensor. So this takes about half a minute for a 1,000 node, 2,000 edges elastic network. And I think the most impressive part of this is it's exact. When I compare, for example, a cubic lattice network with the one in the literature, I really find that numbers are exact, which cannot be done if you have a finite string. Cool. So I want to show some of the cool things that we can also do if the string is not infinitesimal but finite. Because our simulation box is very flexible, we can really give the box a 10% dilation or 20% shear, all those kind of things. And what's cool about biopolymer network is that they do this thing called string stiffening. So even if all the edges themselves have a constant Young's modulus, if they assemble into a biopolymer network that's pretty random, then we find that, like our experimental colleagues find that their elastic modulus increase when the material is subject to some finite strain, even if all the edges are Hookean springs. So we can use our package to test if that's true. So here we have stretched our box. We give it a uniaxial strain. And as we can see, the moduli really increase, the shear modulus really increases. So this is because in the undeformed biopolymer network, the edges are arranged pretty much randomly, and they can take all kinds of orientations. But when we give the box a strain, then as you can see, many of the edges are oriented, they have oriented themselves along where the strain comes from. And all these notebooks have been uploaded on GitHub. Cool. So in the next half of this talk, I want to show research that has been enabled by this package. It's called rigidity homeostasis of the actin cortex. And of course, as I just mentioned, the actin cortex can be modeled as an elastic network. So so the big question is, can we learn from biology to build functional metamaterials? So now we are learning from what the cell is doing. And interestingly, this actin cortex remains rigid even as its architecture constantly changes. So if you imagine you are living in a house where the columns and beams are constantly flying around, assembling and disassembling themselves, you might think it's not a safe house to live in. This house will break down anytime. But this is exactly what the cell is doing. So there's a lot of turnover on the assembly and disassembly of edges and binding and unbinding of the nodes. And what's another cool thing about the cortex is that it maintains rigidity even if its main coordination number is below the Maxwellian isostaticity. That says you need 6 edges per node to be rigid in 3 dimensions because you want to constrain left, right, up and down, forward and backward. Yeah, but the actin cortex only does this maintains rigidity with only coordination number between 3 and 4. So it does something similar to the diamond network that we have just seen. It uses pre-strain. So when the filaments have been assembled into the network, then it's already under some strain. And it's also regulated by many actin-binding proteins, such as motors, that inject energy into the network. And filaments and cross-linkers are undergoing fast remodeling. So every 30 seconds, the cytoskeleton rebuilds itself. So this package actually enables us to build a network model that behaves like the actin cortex. So because we have high flexibility to change and to edit the topology, this is possible in Julia. We are able to build this network that contains all the dynamic ingredients. So we find that this set of ingredients will work to create a network model that behaves like the cell. So firstly, we have mechanosensitive disassembly. So if an edge is under low tension, then it will be split from its corresponding node because the cell decides that, oh, this edge is not important for my rigidity, so I will may as well recycle it. So we really, our experimental colleagues have found exactly this mechanism in the cell. And we also need a small fraction of random disassembly. So all nodes can be randomly split, and all edges can be randomly pruned away, regardless of the tension on them. And of course, we need an opposite process of assembly and energy injection. We believe that this comes from the motors that strains the edges. And lastly, we need some steric repulsion. So I was in charge of the nodes behaviors, and my colleague Marco is in charge of the edge behaviors. And what we find is that we can really build an elastic network that models like the cell. And some qualitative behaviors of these simple models match those in the cell. For example, we see exponential decay of node labels. So in experiments, you can also label the nodes fluorescently. And they also see exponential decay. And really cool, these networks maintain rigidity even if their architecture constantly changes. So this is for the node model, and this thing is for the edge model. And if you look at the mean square displacement of the nodes and edges, you find that they increase linearly in time, which means the network is behaving both like a solid in the sense that it maintains rigidity and has elasticity, but at the same time it's behaving like a liquid in which all the network components diffuse. So these guys run in less than 24 hours to perform like 20 times of turnover. Oh, cool. Well, this is still in its primitive stage. This package is in primitive stage. So in future work, of course, we want to consider other boundary conditions other than periodic, and 2D networks, as well as nonlinear edges and bending rigidity. So please consider collaborating us or contributing to the package. And I want to thank my advisors, Andrea and John, and our collaborator, Marco. And we have our preprint that will come out in August. So I'm supported by the Center of Soft and Living Matter, as well as MERSEC. So thank you very much.
Yeah, we have time for questions.
Hi, thank you very much for the great talk. I just wondered at the end with the dynamics, is it possible to also apply like external pressures to the cell?
Yeah, so currently the pressure or the strain to the cell is held by the periodic boundary condition. And we know that it's not what really happens in the cell. So in a real cell, the network is held by the membrane. There are proteins on the membrane. So that's our next step. We will consider other boundary conditions than periodic.
Thank you.
Yeah. And we are going to apply force field that, yeah.
thanks for the great talk. I was wondering, so I think internally you're using kind of graphs to represent the topology.
Yep.
Do you have any issues when kind of adding and removing, or I guess specifically when like removing nodes where kind of you might have things that are referencing the old node and you have to kind of like change the IDs around and stuff?
Yeah, that's a great question. So for graphs.jl, when you remove a vertex, I think it brings the last vertex into the place. So if you remove vertex 10, then the last vertex becomes the new vertex 10. And I didn't find this out until like midway through my coding. In my developmental stage that has not been uploaded, I'm giving each node unique ID so that we can keep track of the nodes and edges. So this will be in the release version soon.
Yeah. Have you heard of like these generational indexing kind of strategies for that?
I simply generated a random string for each edge and each node. I'm not sure if that's the best way.
Okay. Yeah, you might want to look into like these generational indexing.
Thank you very much.
Yes, really nice talk and visualizations. One thing I was wondering is looking at like centrality measures of the, like if you view the whole thing as like a network, is that useful at all for like analysis?
Yeah, I think so. I think that's extremely useful. And I really want to, I'm pitching to Andrea, and I want to do that. So this package allows us to analyze anything about the network because we have the graph associated with the network, and we can analyze them. And one thing I'm thinking is that you want to analyze how many triangles are there in the network, because the more triangles, the higher the shear modulus. Because a triangle is so stable. So that's one thing I can think about.
Cool. And then also, what did you use to make like those 3D like animations, like with all the like strings and stuff?
This is converted to Mathematica.
Okay.
But I also have a simpler visualization tool in the package itself with Mickey.
Thanks, really cool stuff. So two, I think, well, first question is definitely quick. Do you also support, so you mentioned Hookean springs. Do you support or have plans to support like nonlinear elastic models in the package?
Yeah, I'm thinking about them, and I think a little bit meta-programming is needed because now for linear, for harmonic springs, the gradient and Hessian can be done analytically. So I asked ChatGPT to give me the Hessian, and it worked. And for an arbitrary function of the spring, we need some meta-programming to get the analytical Hessian and gradient.
Sure, or potentially AutoDiff could do that for you as well, right?
AutoDiff is unfortunately slow compared to the analyticals, but it's doable.
Yeah. Makes sense. And then this question very much motivated by the fact that I was sitting here knitting during your talk. I'm curious on the idea of, this is more a technical question, not so much related to the coding part. What you mentioned like modeling knitted fabrics as elastic networks, and it strikes me that like thinking about how knitted fabrics deform, very often there's like a sliding mechanism, right? Where the yarn in different in different parts is sort of sliding across, and I'm wondering how would you map that onto like your sort of node and edge kind of construction, I guess.
Yeah, I would think you can. I'm not sure if you can slide on. You can certainly slide on a straight edge. You just give it a lambda and like adjust the rest length. And for more complicated thing with bending, I'm not sure how to do that.
Yeah. Well, anyway, it's all very cool. Thank you so much.
Thank you very much.
Right, let's thank our speaker again.
Okay.
And also I want to thank all the speakers in the morning session. Yeah, so this concludes the first session of our mini symposium. We will resume this afternoon 1:30 at this room, the same room. So thank you all for coming and hope to see you this afternoon. Thank you.
from the CMU Departments of Chemistry and Material Science and Engineering, and also briefly plug the Julia Molsim organization on GitHub and Zulip instance and all of these wonderful things, which I think hopefully can be a great place for folks to stay connected and continue some of the conversations that hopefully we get started today. Logistically, I think people kind of know the drill by now, third day of the conference, but I'll be chairing this session, and I have, for the speakers, I have time cards that I'll hold up according to how much time is left in your block. And let's also make sure, so we'll have Junchi here running with the mic for questions, so just wait until the mic gets to you with a question so that we can make sure that it's all heard on the stream as well. Okay, and I timed that pretty well, so with that, I will turn it over to Benjamin Coe instead, who will tell us about Smoky Suite, simulating strongly correlated quantum systems. Take it away.
Thank you. Yes, today I will be discussing Smoky Suite. As she just said, I've been doing this work at the University of Tennessee, Knoxville. And to just make sure I don't run out of time at the end or anything, I want to start with my acknowledgements. The initial development of Smoky Suite was started as a postdoc in Professor Steve Johnston's research group at the University of Tennessee, Knoxville, and was funded by the Department of Energy. I also have to call out these three graduate students, James, Sohan, and Andy, that were incredibly patient guinea pigs, testing all of my software and using it in their research and helping me discover all the bugs. The current and ongoing research is funded by the National Science Foundation and the Simons Foundation. I'd also like to thank three other PIs for helping a lot. Professor Richard Skalatar at UC Davis, Dr. Thomas Meyer at Oak Ridge, and Dr. Kipton Barros at Los Alamos. Some of you might recognize Dr. Kipton Barros. He's also an advocate of Julia and is the lead developer on the sunny.jl package. So what is Smoky Suite? Where does the name Smoky come from? It's a rather silly play on words. This work was done in Tennessee, and right near my university is the Smoky Mountain Range, named for the beautiful layer of fog that always lays over it as pictured here. So we sort of named it after that mountain range. But what is it in terms of what I work on? It's a GitHub organization hosting a variety of Julia packages focused on simulating strongly correlated electron and phonon models, think interacting type binding models. And it focuses on sort of the overarching theme is methods related to something called quantum Monte Carlo. We've sort of pursued a modular or tiered development philosophy where I've tried to break the packages into three categories, roughly speaking. There are your high-level packages, which I'll mainly discuss Smoky DQMC in this talk, but high-level packages are meant to these are what you use for a research project that will hopefully result in a publication, they give you all the bells and whistles. Lower level packages are intended to sort of make implementing some specific many-body numerical methods simpler. For instance, all four of these packages were used to implement Smoky DQMC. And then utility packages are packages that implement and export functionality that might be useful in a wide variety of contexts. Perhaps the clearest example of this is lattice utilities. It was the first Julia package I ever made, and it's for just representing arbitrary lattice geometries and automating the process of building neighbor tables. And I have to say, I really like doing it this way, because now all the graduate students I work with use this package when writing their own classical Monte Carlo codes or ED codes on their own. They find it really useful. And then these two grayed out ones are planned future development work. And then I should mention all of these packages are registered, and you can just install them using the package manager. And with that, I have to give a shout out to the package manager. I'm not a software engineer. There's no way I could have sort of developed software using this tiered framework if I had to manage all the dependencies myself. It would have been a nightmare. I'm not that competent. So I'm really grateful package PKG exists and takes care of all of it for me. So what is Smoky DQMC? We published it as a SciPost code base last year, and it's a package for performing something called determinant quantum Monte Carlo simulations. These are equilibrium, finite temperature, grand canonical ensemble simulations. And it supports a pretty broad class of Hamiltonians. This is a really big, ugly equation. I just kind of put it up there for you all to look at. But more specifically, it supports second quantized electron type binding Hamiltonians with both local and extended repulsive and attractive Hubbard interactions. very flexibly parameterized electron-phonon interactions, and it can run simulations on arbitrary lattice geometries. For those of you unfamiliar with the word phonon, think of the normal mode vibrations of a crystal, and then you quantize them. Those quantized vibrations are what we call phonons. And as you can imagine, the conduction electrons in a material will interact with the vibrations of the atomic nuclei in that solid. And so we might want to simulate that. So this package supports a very wide class of those types of interactions, allowing the phonons to couple to both the electron potential energy and its kinetic energy. While we only published this package last year, it's already been used in quite a few publications. I have to particularly shout out the green ones because these are by research groups where I don't know anyone there. And so I actually discovered this when making this slide, that people had picked up this package and used it in their work. And that was very exciting. I was like, I don't know these people. That's so cool. So yeah, I had to shout that out. And then just for my own edification, I had to show one cool figure from a recent publication. It's this recent PRB. This is a paper looking at a simple model for graphene where you can imagine the carbon atoms vibrate in the plane of the graphene, and as they move closer or farther away from their neighbors, it becomes easier or harder for the electrons to hop from one atom to another. And this results, if the interaction becomes strong enough, in something called a Kekuli valence bond phase, which has been observed in strained graphene samples. And what you see here is the ground state and finite temperature phase diagram. And the KVBS phase is sort of pictured here. It's this alternating pattern of expanded and contracted hexagons. And on the right here are histogram plots of the sampled order parameter as we lower the temperature. And as you can see, at high temperature, it's centered near 0, and then at low temperature, it forms these 3 lobes, signifying the fact that the KVBS phase breaks a Z3 symmetry. So I'm really just showing this to you because I think it's a cool looking figure, but I had to plug some of the recent research. So I've mentioned that Smoky DQMC does something called a determinant quantum Monte Carlo, or DQMC simulation. What is DQMC? Like most quantum Monte Carlo methods, it starts with the partition function, and then we re-express this partition function as a path integral in imaginary time, where or the inverse temperature, where we discretize it using this step delta tau. And then there's a lot hidden in this approximation here, just high level discussion. Sort of 3 things happen in a row. We apply something called the Suzuki-Trotter approximation to separate the non-interacting and interacting parts of the Hamiltonian. Then we do something called a Hubbard-Stratanovich transformation to decouple the interactions. And then having done that, we integrate out the fermion degrees of freedom. That's a lot of complexity. At the end of the day, what you're left with is something that looks like this, where X denotes all the different types of degrees of freedom you might want to simulate. In my case, Hubbard-Stratanovich fields or phonon fields, and W is the weight function in our Monte Carlo simulation. And in literature, this method is popular because it's a well-controlled approximation in the sense that we can choose what value of delta tau we want to use. And in practice, we make it so small that any bias is much smaller than the sampling error. So for our purposes, people like to call it numerically exact. That's not really true. It's numerically exact in the sense that it's a well-controlled approximation that we know will converge to the correct result. Where does the word determinant and determinant quantum Monte Carlo come from? Well, it comes from the fact that our Monte Carlo weights in the simulations can be expressed as products of matrix determinants, pictured here on the left, where each of these matrix Gs are represented by a product of B matrices, propagator matrices, then you add the identity and you invert it. The number of these B matrices is proportional to the inverse temperature. And then, like any other Monte Carlo simulation, you, even classical ones, you make measurements for each sampled state, you measure some observable O, and then at the end of the simulation, you average them to get a final prediction for the expectation value of that observable. Again, W plays the role of the Monte Carlo weight. So some comments about DQMC as a numerical method. These G matrices and B matrices are n by n, where n is the number of orbitals in your finite lattice. So DQMC has a computational cost that scales as beta n cubed. So it scales cubically with the system size and linearly with the inverse temperature. One issue that makes DQMC kind of infamous in our community as being a really, really tricky algorithm to implement is that if you were to just naively apply the formulas, you would get garbage. This is because these Green's function matrices tend to be very poorly conditioned, and in particular, multiplying this long chain of B matrices together that are all themselves matrix exponentials, then adding the identity and inverting it is an incredibly unstable numerical procedure. You'll get nans and infs running all over the place really fast. So to deal with this, you have to, behind the scenes, do a lot of fancy numerical work using QR decompositions to try and stabilize this calculation. And so this is what the stable linear algebra and JDQMC frameworks, these lower level packages I previously mentioned, actually take care of. So then these packages are meant to make writing new DQMC codes simpler. And I use them to write Smoky DQMC. The other thing, when I was starting as a grad student, I was incredibly naive. I was like, when you do a simulation, you just have access to the system. Making measurements should be trivial. That's not true. Making measurements is actually really hard and tedious to do correctly because it involves expressing everything in its Wix contracted form, and it's just complicated to implement without little mistakes. So all of that I actually also offloaded to a separate package called JDQMC measurements, which implements a variety of frequently used correlation measurements for arbitrary lattice geometries. And then lastly, I like to be transparent. I'm not going to dwell on this for a lot, but some of you familiar with quantum Monte Carlo might have heard of the sign problem. This can generically arise. We like to think of this W as being our Monte Carlo weight, but for most systems, it can actually go negative, which makes it really hard to interpret as a probability. And so we have to deal with this by doing something called reweighting, where we do our Monte Carlo simulation with respect to its absolute value, and then observables are given like this. And in practice, this can result in an exponential slowdown because it becomes a really, really bad signal-to-noise ratio problem. So in practice, we tend to focus on doing DQMC simulations of systems where there's some underlying symmetry that we can exploit in order to avoid the sign problem from occurring. So I sort of explained really quickly 1,000-foot view of what is DQMC. Why is Julia so good for DQMC? Well, DQMC is expensive, and you need a fast language. For context, to generate, like in most of my research, DQMC simulations that we need to perform take on the order of, I don't know, a few days to a week, even more than a month sometimes. And that's if you implement them in C++ or Fortran. So Python's just kind of a no-go. Also, scientists are not software engineers, and science graduate students, the people usually running this code, are especially not software engineers. That was especially true of myself in graduate school. The number of hours I wasted trying to get my advisors for Tran 77 DQMC code compiled on various clusters and properly linking to BLOS and LAPACK is rather embarrassing. So Julia avoids a lot of this. So Julia provides a lot of solutions. It's fast, it's easy to install, setup is trivial with the package manager. Of utmost importance to me is the fact that it ships with the BLOS and LAPACK. I love that. And then it has all of these amazing tools like Documenter and Literate for creating useful documentation, excellent unit testing tools, and great tools for benchmarking to make sure your code's fast. I just had to shout out some of my favorite packages here that I use to make development easier. And then lastly, there's also PKG templates that allows me to masquerade as a software engineer of middling talent, in that if I had to learn how to write YAML files to set up the GitHub actions to have continuous integration so all of this happens automatically, I never would have figured out how to do it on my own. And PKG templates takes care of a lot of that. So a lot of this development work is possible because of the Julia ecosystem that I can leverage. So why Smoky DQMC in particular? It's important to first acknowledge what was already there. The best code out there for doing DQMC is ALF, developed by Professor Assad's group in Germany. And it is a very flexible, performant code. It's also a Fortran code that is rather annoying to set up and get running. And you kind of have to like go to a summer school they run to learn how to use it. At least the docs, I have a hard time parsing the docs. There's an even older Quest code that my advisor wrote, also written in Fortran. And then there are a whole bunch of bespoke C++ and Fortran codes floating around. So that was sort of where Smoky DQMC comes in. First of all, some novel features. As I said, we can do really flexibly parameterized electron phonon models. And this is made possible by the fact that we use highly optimized hybrid or Hamiltonian Monte Carlo sampling schemes for the phonon fields. It uses a flexible scripting interface like many Julia packages like iTensor and many that we all use. It has extensive documentation that takes a lot of time to make, as I'm sure a lot of you know. And then there are a lot of tutorials with also support for MPI parallelization and using MPI.jl and robust checkpointing with JLD2. And there are tutorials that sort of walk you through how to like set up a basic simulation, then add MPI parallelization, then add checkpointing. So it's like incrementally adding more and more complexity to the simulations. It's finally ending you up somewhere with something that you can use in research. And then there are tons of additional examples with less explanation, but are still hopefully a template for people to get started from. All the data is stored using HDF5 files with convenient functionality to export to CSV. And then there's kind of this novel functionality where we can tune the chemical potential during the simulation to achieve a target density. So this, in practice, saves a lot of time. So yeah, Smoky DQMC scripts. I really want to emphasize the fact that like everything else out there is like write a configuration file, often like a very bespoke configuration file that's annoying to have to learn how to use. Smoky DQMC then instead has you write your own scripts to run simulations. This block of pseudocode is from our SciPost paper that one of the referees suggested we added, and was actually a very good suggestion. It's basically sort of like a 1,000-foot view of like what is the structure of a DQMC simulation. And it's basically identical to any other Monte Carlo simulation. You initialize your system, you perform some thermalization updates, then at some point you continue updating the state of your system, but you also start making measurements. You periodically write some of these bin averaged measurements to file, and then after the simulation's complete, you sort of process the results. These scripts are really meant to reflect this structure and give people insight into the internals of it. So there's a lot here, but you can see there's a for loop. Iterate over the number of thermalization updates to perform. Then you perform an update. Then there's another for loop a little further down that says iterate over updates and make measurements. You make a measurement, you update your system, you make a measurement, you periodically write it to file. It's all pretty transparently there, and people can sort of like, once they figure out how it's structured, modify it to their own needs. And that's been sort of fun to see people like take these scripts and modify it however they want to like fit their specific workflow. I've also discovered though, that as a researcher, my imagination is rather limited. As soon as I made Smoky DQMC, I had colleagues coming to me at the university and at other locations being like, this is really cool. Can we do this model? And I'm like, no. While it can do a lot of interactions like local and extended Hubbard and electron phonon, people come with like the craziest model Hamiltonians that like I have never heard of. And they're like, can we do like 20 spin species? Can we do like crazy spin orbit couplings? And I'm like, no, I'm sorry. But with that in mind, again, I mentioned this JDQMC frameworks package. It includes a tutorial on how to write a DQMC code from scratch. And so I'm hoping that like even if Smoky DQMC doesn't meet your needs, if you're motivated enough and it's important enough to you, you can sort of more quickly write your own DQMC code using this package. And I actually think this would be a great place to try and like link it with something like the Carlo.jl package we heard about. So maybe we can try reworking this tutorial to use Carlo.jl. So that was Smoky DQMC. What is Smoky Deek? There was one other high-level package, and I want to go through this one really quickly. The lead developer on this was the graduate student at UTK, James. and it stands for Differential Evolution of Analytic Continuation Algorithm for Noisy Quantum Monte Carlo Correlation Data. That is a mouthful. So in DQMC and other quantum Monte Carlo methods, there's this common problem that arises when processing data that you want to do something called analytic continuation. What is analytic continuation? What DQMC spits out are measurements of correlation functions in imaginary time. And here's the electron Green's function in imaginary time. This is not something an experimentalist can measure. What an experimentalist can measure is this guy over here, the spectral function, which becomes the density of states in the non-interacting limit. You can measure this using like ARPES experiments and other photoemission experiments. So we have this. If you had A of omega, calculating G of tau is trivial. Doing the inverse, especially when your signal is noisy, is an ill-posed inverse problem, and it's very tricky. So here's sort of an example to demonstrate that. Here are two curves, blue and red, for G of tau that came from two different quantum Monte Carlo simulations using two different algorithms. They agree to within error bars really, really well. Even so, when you try doing analytic continuation on them, you get something like this, where while they're similar, there are important differences. And the fact that like there are two peaks here really does reflect real physics that we were expecting to see, but one of them, like the AC, the analytic continuation, didn't work well enough. So Smokey Deek exports one specific algorithm for addressing this problem. And just to give you a flavor of what it can do, here's an example of a plot generated from DQMC data using Smokey Deek. So these were simulations of something called the Holstein model. And as you lower the temperature, a charge density wave phase opens, and at the same time, a gap opens at the Fermi surface. And what you see here is the momentum resolved spectral function, and then the integrated spectral function here. And the gap opening, again, signifies the formation of this charge order. So this is like the sort of problem it's good at addressing. And lastly, I want to shout out two other registered packages in Smokey Suite related to the analytic continuation problem. So Smokey Deek, this Deek algorithm is one algorithm for doing analytic continuation. There are many algorithms for doing them. There's stochastic analytic continuation, maximum entropy method, the PAD-A method. There's a zoo of them. I wrote a package called Smokey Synthase, which basically allows you to generate synthetic quantum Monte Carlo data with noise. So then you can use that package to benchmark different types of analytic continuation algorithms against each other in situations where you know what the result is. And then additionally, there's this package called Smokey Hankel Correlation Cleaner. Last year, Professor Gohl released this really cool paper where he introduced this algorithm for denoising noisy imaginary time correlation data generated by a quantum Monte Carlo simulation as like a pre-processing step. And as soon as I saw this little algorithm, it wasn't that complicated to implement. I was like, I should make a little Julia package to do this. So that's what this package does. So I am going a little faster than I expected, but I want to briefly go over the development roadmap. So right now, I'm working on a 2.0 release of Smokey DQMC. If I'm being brutally honest, this is happening sooner than I wanted it to because I made some not great design decisions, especially with how data was written to file. I didn't know like file quota limits were a thing, and that's been screwing over a lot of the graduate students I work with. So I had to go back and like rework how data is written to file, and I'm switching over to HDF5 files. But once I decided to do that, I'm like, this is gonna be a big breaking change. I might as well add a bunch of new functionality at the same time. This includes new Hubbard-Srutonovich transformations for decoupling the local Hubbard interaction, support for extended attractive and repulsive Hubbard interactions, and then also support for something called twisted boundary conditions. Next, the NSF is funding the development of this extension package for Smokey DQMC called Smokey ELF QMC. So the idea is it extends the functionality of DQMC. It will only work on Hamiltonians that don't include Hubbard interactions, but just electron-phonon interactions. But by limiting yourself to that class of models, you can use a modified quantum Monte Carlo method that scales linearly with the system size, allowing us to access larger systems. This was actually like my PhD thesis, and I wrote it in Julia, and now I get to do like a good version of it, which is fun. And then lastly, I'm working with Dr. Thomas Meyer at Oak Ridge National Laboratory, going to be working on implementing the dynamical cluster approximation algorithm, which is a cluster extension of dynamical mean field theory, where we use the DQMC implementation in Smoky DQMC as the cluster solver. And this will allow us to do DCA calculations with electron-phonon interactions, as well as get linear scaling and beta, where the existing methods usually get beta cubed scaling. So yeah, that'll be useful. So that's the end of my talk. Thank you. And if there are any questions, happy to field them.
Thank you very much. That's very cool stuff. Do we have questions from the audience?
Cool, yeah, that was a really great talk and overview of the physics as well. I was wondering for the sign problem, have you looked into like Langevin, I think it's pronounced Monte Carlo? Or like stochastic quantization is like another word.
I haven't looked into, I've read the papers about that stuff. That's some pretty heavy work, and I think to like implement that myself, that's like give me a year and I'll work on it.
Yeah,
there's some other cool methods. One of the people in the audience is doing something called constrained path quantum Monte Carlo to address the sign problem. But yeah, that's a good question. I would love to work on that at some point, but man, I don't have the time.
Yeah, there's not good code for that online or too much. And then also for the inverse problem, is it just like additive, you just assume like additive Gaussian noise? And do you estimate like the covariance matrix for that?
So what we do is I actually stole, Professor Sandvik at Boston University a few years ago wrote this PRX where it doesn't mention analytic continuation, but hidden in the appendix, he introduced this method for generating synthetic quantum Monte Carlo data where you add noise, but you add it in such a way that it's exponentially correlated in imaginary time. And he showed that this sort of mirrors how noise looks when generated by a real quantum Monte Carlo simulation. So that's what the Smoky Synthase package does. And it like links up with like the distributions package. So you can define a spectral function using the distributions package and then treat that as your spectral function and then calculate the corresponding G of tau curve and add noise to it using this technique.
Cool, so someone could like just work on the inverse problem even if they're not an expert in like the physics part.
Exactly, and
cool,
in fact,
cool.
I'm working on some people with that right now, and it's kind of like this tool is great for benchmarking different algorithms and optimizing.
Oh, cool, thanks.
Yep.
Thank you for the talk. So I work in quantum computing topic, and I'm curious, following up on the sign problem, could you maybe help us maybe comment on what kind of problems should we as people in quantum computing be looking for if we want to find hard instances where techniques like this would struggle?
So, you know, I love DQMC. It's like my workhorse. But if you were to write, but in truth, like 99% of Hamiltonians out there have a sign problem. It's actually the exception that there's not a sign problem. Usually you have to have some sort of underlying symmetry in the model, like particle hole symmetry, or in the case of electron phonons, like the phonons couple to spin up and spin down symmetrically, such that G up and G down are always equal to each other. But in general, for most interacting Hamiltonians, you can imagine writing down, this is not the case. And as soon as that's not the case, you will in general expect a sign problem to emerge. In any of those problems, like there's a limit to how far we can go with DQMC if we don't use some other approximation to help push us along.
Okay, thank you.
Yeah.
Oh yeah, I have a quick comment on that question. I think the connection between quantum computing and quantum Monte Carlo gonna significantly speed up the quantum chemistry or quantum physics calculations, because there are already people starting doing development that optimize the wave function, figuring out the nodes of the wave function from a quantum computer, and then ported it into QMC as their initial trial wave function to minimize this same problem. So definitely there's a future.
All right, thanks very much. And we're pretty much exactly on time, so well done, everybody. And next, I'm happy to introduce Henry Snowden, who will be telling us about lightmatter.jl, simulation of light-driven hot carrier dynamics. Take it away, Henry.
Yeah, hello. Thank you very much for inviting me, and I hope you don't get too sick of my voice, as I do have 2 talks this afternoon. I apologize for this. But first of all, I'm going to be talking about simulation of light-driven hot carrier dynamics, which basically means the response of electrons to a laser pulse. And if you aren't really aware, we're trying to move towards a green and more sustainable future, and light is a very important part of this because it's very abundant. Obviously, we can source it from the sun, and if we can channel this into chemical or electrical energy, we can easily produce much more sustainable processes for our future. But the problem with this is really designing materials that are very optimal and efficient at this is a great challenge, and this comes down to our ability to sort of simulate their response to the light itself. And for anyone who's not really aware and hasn't studied this field, I wanted to quickly go over the timeline of a light-matter interaction so that you both know sort of what's involved, as well as how long these processes take, and so how long a duration of a simulation you really need to perform. So we obviously start off with an equilibrium Fermi-Dirac distribution. I hope most of you are familiar with this. And when we hit it with a laser, electrons start to absorb photons and enter an excited state. And this generates some electron-hole pairs, cartoonishly depicted as a step, but very rarely actually look like this. And this takes on the order of tens of attoseconds to a few femtoseconds. So very quick reaction. These then start to interact with one another and the thermal background of electrons, and they start to produce a hot electron distribution you can see here, which is just a Fermi distribution at a higher temperature. And this again can take on the order of 10 femtoseconds to a picosecond, but in all metals it will be sub 100 femtoseconds. And finally, they will then go on to interact with the phonons, and now we're into the sub 100 picosecond range. So we need methods that can simulate attosecond processes all the way up to almost, hundreds of picosecond processes. And this needs to be simulated in one process, and that's quite a challenge to do. Why do we need to do this? We obviously want to make use of these excited materials. And in my later talk, I will discuss a little bit about atomistic simulations using laser-driven techniques. But really, there's 3 main ways that an excited distribution can interact with a material or an absorbate on a surface or a quantum molecule in a quantum gate. It could happen via direct excitation, indirect excitation, or spillover into the LUMO. And all of these methods are highly dependent on the current exact electronic distribution in your material, our red thing here, and therefore accurately depicting this is essential if you want to get any level of rates or chemical reactivity correct. And so the aim really of lightmatter.jl was to be able to simulate these processes efficiently and in an open source way that anybody, experimentalists or computationalists, could use to investigate their materials. Now, it's not the first code that can do this, and I think that whenever you start thinking about making a new code, you should first survey what's out there and see if it's good enough. Otherwise, we end up with millions of codes and they all do the same thing. And there are a few examples, including quantumoptics.jl, that I have manipulated to do these sort of things, but they all sort of have issues. Quantum optics, being a full quantum treatment, means that it doesn't scale very well to nanoscale properties that we're interested in. We have other techniques such as ELF-bolt or NTM-Pi that are really limited to one methodology. They can't provide you a list of options, and that I also think is a real issue. And so what lightmatter.jl shines or tries to do is it tries to offer you a multitude of methods and approximations within these methods that allow you to design the exact simulation you want to perform. We make no decisions for you, you get everything you would like. As part of this, we want it to be easily extendable, as if you have any new techniques or methodologies of interest to you, then we want you to be able to easily plug and play them in and start to mess around with it. And again, we really don't want to limit what you can do. And then finally, we want it to be extendable enough that it can model a wide range of systems of varying complexities, including surfaces, alloys, whatever it might be. We really don't. We want to expand far beyond anything that is currently possible. Julia can assist with this. It is a very powerful tool, and there's 3 main ways. First of all, metaprogramming with expressions is an incredibly cool tool that we have fallen in love with recently for assembling your equations and your functions on the fly. We use generalized generated along with the metaprogram tools directly in Julia to physically step-by-step Lego block assemble exactly what you ask for in equation form, and then provide you that function to then propagate through ordinary diffie-q or whatever else you like. The flexible and high-level code structure of Julia also makes it so that anyone with very little experience in code can somewhat get to grasp with the package. I really like that. I mean, maybe some people will get mad at me here, but the code is quite Pythonic in the way it looks, and everybody knows how to write Python code. Find someone who can write Fortran 77 code. And finally, the multiple dispatch and nested structures allows us to do these complicated systems without limiting to is it this system or if else sort of statements that might limit performance. The current methodologies that we obviously want to potentially implement are the 2-temperature model. Any engineers will be very familiar with this model if you're interested in this field. All it does is it says your electrons are a temperature bath, your phonons are a temperature bath, your electrons get heated up by a laser, and then they sort of cool down. This is extremely cheap because it's extremely classical and sort of basic, and so you can do huge spanning complicated structures, multi-dimensional, whatever you want. But this comes at the cost of really none of them electron-hole pairs that we might be interested in. The other side of that coin is time-dependent density functional theory. This is what I call the quantum approach to this problem, and it provides very accurate electron-hole pair generation at a significant cost, but it is unfortunately unable to capture electron-electron scattering at all, really. It puts electron-electron scattering on the same sort of timescales as it does the electron-phonon. And this means that these non-equilibrium electrons are living far too long, and any resulting reactions you propagate the rate will be completely off. And finally, what I consider to be the state of the art is the Boltzmann equation. This provides accurate dynamics of the electron and phonon distribution, but it is excessively expensive, like beyond belief, at least in my opinion, which means you cannot go beyond a 0D, very simple system with no sort of added complexity external fields. It blows up to in expense far too quickly. And before I could even make this package, I had an issue, because I wanted the speed of the 2-temperature model and the ability of the Boltzmann equation. And so I wrote like 4 lines of Julia code and then went over to a chalkboard and along with the Rethfeld group built a whole new theory of light matter interactions to accomplish this problem. And for the next 5 minutes, I'm going to briefly introduce this. So if you don't care about physics, just go to sleep, that's fine. So the athermal electron model takes this sort of total electron distribution you might see from a Boltzmann calculation and sort of just cuts it in half. This is a very nice feature because now we have a thermal distribution that we can represent as a temperature, and this difference from our true distribution, our electron-hole pair distribution. As we have a temperature system, we can treat this as a temperature system, and I've made a 2-temperature model. Woohoo, it's cheap. Now, if I just plug on an electron-hole pair distribution and add a few approximations on top, this becomes this little assembled system that is much cheaper to run than a Boltzmann equation, and therefore provides me the flexibility to go bigger, harder, and more complicated than we ever really could before. And as well as this idea of plugging an extra system on top is what then motivated the design structure of light matter. We wanted to just plug things on top of other things, or insert approximations in places. And so how light matter is really designed is that we provide you with these building blocks, some electronic systems, some phononic systems, and some structural choices that you can make. You just say, I want this and that and the other, and it builds a simulation. And just to quickly, or to show you sort of how this process works, to build a very simple 2-temperature model, we first are going to design a laser. We're going to choose a Gaussian laser because everybody does. We're going to give it some parameters. This all works with unitful, so you don't really have to care about units because units are annoying. We're going to build an electronic and a phononic temperature by setting them to true, coupling them, or setting the couplings to do, giving a couple of approximations and the relevant parameters. Pop that all into a simulation object, and we're done. We have now built a 2TM. We can ask the system for the equations, and this is the equation of motion for the electronic system. It looks like a mess because the other thing I realized was expressions look like a mess very quickly and become quite hard to read, but that's fine. You'll figure it out. And we set some initial temperatures, a time span, and then we just run our simulations. It's all plumbed through diffeq, so all the keyword arguments, all the algorithms that work there also work here. So you really can go straight out the box. And we have some post-processing stuff, saving as a HCF5, and there's a whole host of different functions or symbols you can place here to get internal energies out or various different properties to make your life a little easier. We can then obviously get the results from this. This helps you by just breaking them all down into nice vectors and matrices. Otherwise, they can be quite awkward as we use recursive array tools under the hood, and this produces quite awkward solution objects if you ever try to do that. And what you produce is a 2-temperature model curve. Here, it doesn't move down very far because I simulated gold, and gold doesn't have much of electron-phonon coupling. And so if I really wanted to get this to go into equilibrium, we'd be going for like 20, 30 picoseconds. And this is part of the problem. We wanted something that could really scale, because if you want to go 20, 30 picoseconds, I will show you some computational costs later, but Boltzmann isn't going to do this. To include athermal electrons, all we have to do in the systems we've already defined is define a photon frequency and just say that they're now coupled to athermal electrons. And now these baths will go, okay, I'll just assume that's there. We need to define an electron distribution to propagate over, a density of states and a geometry, just so that it knows what the electronic structure of your problem, and build an athermal electrons. Unfortunately, this is a bit more complicated, but you again set it to true, set all your couplings, set your approximations on how you want things to relax, and then give it the relevant parameters. It's the same process all over again, and now if we plug all of this into our sim, we now have an athem model rather than a 2-temperature model. We could have substituted all of this out for an electronic distribution object and a phononic distribution object, and we'd have a Boltzmann equation. And you can really just pick and play however you choose, and it will build whatever you want. And here is the difference in results. There's a slight decrease in temperature because the temperature is now stored within our electron hole pairs, and we get access to the actual electron hole pair distribution as a function of time. This is at the peak of the laser pulse. And so this is just the part that's completely missing from your 2-temperature model. Now, if any of you are aware of light-matter interactions, you might tell me, why don't you just use the Boltzmann equation with a relaxation time approach? It's a common approach that's been used since like the 70s, I believe, and I'll tell you because it has horrible energy and particle conservation problems, and I have no idea how no one figured that out. It loses about, I think, over a picosecond up to sort of 80% of the internal energy that was put into it. So it massively bleeds energy as well as particles, and therefore it's not sufficient to capture long-time dynamics. In the short time frame, sure, you could do this, but you can't do this for the 20 picoseconds of gold, and so really we did have to build this whole new theory. Of course, athem does not lose particle or energy conservation. If it did, I wouldn't be here, so, you know, take my word for it, we fixed the problem. And it compares well. In terms of excitation, it is almost exact to the Boltzmann equation. In terms of relaxation, it's not quite so exact to the Boltzmann equation. But all of these calculations, here's the cost. So 1 core and about 2 minutes to perform this athem calculation. This was about a picosecond, and 160 cores and 5 hours to perform a Boltzmann calculation. And this is obviously just going to scale worse and worse and worse as soon as you start to add spatial degrees of freedom. It's just not possible with the Boltzmann. You're going to destroy your entire CPU budget in about 1 calculation. And so just to sort of summarize this model, it really does capture electron dynamics similar to full Boltzmann collision integrals. It does it cheaply and doesn't violate physical laws, which I always like. And if you'd like to find out more about real details of how it works, there is a preprint that hopefully should get accepted into, it's accepted into applied physics, so hopefully will eventually be published one day. And a key part of this method is only publicly available in lightmatter.jl. So anything I'm about to show you with all the cool stuff that we can now do that nobody else in the world can do, well, they could if they went on Julia and clicked add light matter. But without it, they can't do any of this. So I've said we want to go harder and bigger. So how do we do this? So to go beyond 0D, we need to add a fixed law diffusion that you might remember from your physics or chemistry classes, and some ballistic transport on our non-equilibrium electrons. I'm going to ignore phonon transport because it's so slow that I'd fall asleep. And here's the big deal, right? As soon as I go to a 30 nanometer thin film, which after sampling a bunch of literature was approximately the average size that experimentalists were using, I saw a decrease in the surface temperature of about 25%. This is obviously going to be a significant effect if what you care is the energy of your surface. Having 25% less energy at the surface means whatever you think that energy is going to do, it's going to do 25% less, if not worse. And so really incorporating these spatial effects and properties is important into getting realistic simulations of our materials. And to really push this, one thing that you can do within lightmatter.jl is you can give it a range of density of states that correspond to your surface all the way down to your bulk, and you can actually see the effects of changing the electronic structure as you go through the material on your temperatures and spectral densities. Here I've tested a lot of materials and a lot of surfaces, and just given the number of electrons at 1 eV above the Fermi energy, I think at the peak of the laser pulse. And you can see for the most part it doesn't really matter, at least at this energy range, but clearly for ion 111, about a 1.5 times increase in number of electrons is a big deal. And again, this is an important factor to include, and it's not something that you can include or incorporate in anything other than TDDFT and ATHEM. They're the only two methods that could ever capture this effect. And TDDFT is really size limiting. Small nanoparticles, tens of atoms only. You go bigger, it's too expensive. So this is really something that can only be done here. And if you want to do this, you simply just need to tell it now has a spatial density of states, give it a folder where it can find them, and give it a geometry of where you calculate them so it knows the heights that each of these correspond to, and then it will interpolate and map everything onto the grid that you chose. And so it handles everything on the hood to build these more complicated electronic structures for you, so it's no real big deal. And for the conductivity, you set it to true, like everything else, and you give it the respective parameters that it asks for. All of this sort of parameter request is in the documentation, so don't worry about needing to memorize the equations and know what parameters you need. And just to sort of cap off a little bit, I wanted to show an antenna reactor complex because this is a material that is very interesting in plasmonic catalysis at the moment, and is a material that this study we recently submitted to Nature Materials, so it's apparently exciting. And really these materials are categorized by having an optically active material that interacts with your laser and a catalytically reactive material that interacts with that is your surface, that interacts with some adsorbates or molecules or whatever it might be. And so in order to do this, you now really need spatial transport, because physically here, if we want to resolve the difference between our gold and our nickel, we need to be able to say, okay, at this height into our slab we have it's gold, this height we have nickel, and so Boltzmann and any of these things aren't going to be able to do this. And already at this sort of size, we're pushing the limits that TDDFT or anything like that could possibly simulate. On the right, I have the temperature profiles at the surface of the nickel. Unsurprisingly, gold would be the highest if this whole thing was gold, and that would be because it has no electron-phonon coupling, and so it just stays hot forever. Whereas the nickel itself, due to the incredible electron-phonon coupling throughout, if this whole thing was nickel, it would just all go straight into the phonons, and you would have no real electronic energy, and our gold-nickel hits that sort of perfect sweet spot of being quite a lot hotter than nickel, but still reactive and interesting, unlike gold. And we can do the same thing to look at our athermal electrons using the ATHEM model, and you can see a huge spike in comparison to both the gold and the nickel, showing that this material is much better at transporting electron hole pairs to our surface, where they can be reactive and useful, than any either the gold or the nickel on its own. And again, this is very interesting to material discovery or any processes like that. And to do this, we need to add our interface height onto our dimension. We need to tell it that it has two systems, and then all of our material parameters, I've kind of tried to make it simple up here. Instead of just giving it one, we just give it a vector of length 2. And then it knows from this interface and how many systems you have that, oh, that height denotes to that a parameter, that height denotes to that parameter, and so it then again handles everything under the hood for you to build much complicated systems. And you could even go all the way up to building photovoltaics, where you have all the different layers involved in a photovoltaic stacked on top of each other, hit the light on one side, and watch how the electrons move all the way through all of them, and it could all just be mapped out directly through Atom and through lightmatter.jl. And so these were my aims, really, and I thought I would just come back to them a little bit and discuss sort of how we're doing on each of them. Oh, apparently not. So light matter includes methods from all levels of theory. We do have a dipole approximation density matrix approach. It's a little bit work in progress, so don't expect it to be too accurate just yet. All the way down to our classical 2-temperature model, we can do it all. Adding new methods is literally as simple as defining a new keyword argument or changing the symbol in that conductivity approximation or whatever it is, and making sure all the relevant parameters are there, building a new expression, and it all works throughout. And we've already shown that you can implement methods to capture a wide range of complex systems and ten-react complexes. You can look at surface effects. And like I said before, this is all stuff that until now has not really been feasible. And so hopefully with future development, this package could become very interesting. And I will say it's only a year old, so let me off on the docs and tests. It's not quite there yet. So thank you very much for listening. I hope you're not too bored of my voice yet, because in about an hour you've got me again. I'm so sorry. And if you want to learn more, there's the GitHub link.
Thanks very much, Henry. Do we have questions from the audience? We have plenty of time.
Thank you for that very interesting talk. I have a question about your electron-hole pair treatment.
Yes.
Do you include screening between the electrons and holes, or you treat them as independent particles?
Do I include spin?
Do include screening?
Oh, screening. So at the moment, we kind of treat them as independent particles, but there is already methods sort of being developed to include more complicated matrix elements in how that excitation is done. One of my aims is to use TDDFT to actually get the matrix elements straight out, and that way we should be able to reflect exactly TDDFT's electron hole pair excitation profiles, so that amazingly good at it no longer becomes true, it becomes equally good at it, and use that to then drive our electron hole pair generation. Okay. So it's possible, but not yet.
So just to clarify, the pair density of the electron hole pair that you showed, so that is an uncorrelated density then?
So it's uncorrelated in the sense that the excitation isn't screened based on the particles, but it's correlated in the fact that it is scattering among the other particles, and it's correlated in the fact that in the Fermi's golden rule expressions we use, it does incorporate things like Pauli principle, etc., to ensure.
Yeah, but the pair density you will be able to factorize it as an electron density or a quasi-electron density times a quasi-hole density.
Yes.
Thank you.
Thank you for the talk. In the athermal electron approach,
yes,
you split up the density into two parts, the thermal and the athermal, right?
Yes.
How do you choose the temperature for the thermal part?
So what we do is we choose it to start out as the starting temperature, and then we use a 2-temperature model with an addition. Rather than using a laser source term, we say that the energy into this system is the energy given out by scattering here. So this term represents scattering of the electron hole pairs with the thermal system, and any energy lost from here then gets, through this process, then gets moved into here and then converted as a temperature.
I see, I see.
Yeah, a related question, to what limit or extent this separation breaks down?
Okay, so there's two main approximations. So, this separation it can be derived exactly. There is no actual issue with separating it. because you're just saying that my distribution is a sum of distributions. And if you were to include all possible interactions between these systems, then it would still be analytically exact. The only place that this really breaks down is, for simplicity's sake, we actually say that currently the athermal electrons don't scatter with themselves, just because there's, at any one time in a realistic system, there's so few of them that this scattering is minuscule in comparison to the scattering with either the phonons or the temperature system, and therefore we can just save one extra step of calculation.
So you mentioned photovoltaics as well, which is a subject near and dear to my heart because that's what I focused on during my own PhD. And I'm curious, so your examples here were all with lasers, which of course we presume are monochromatic or close to monochromatic. Are there any particular complications that would arise if you're talking about excitation with like a solar spectrum, for example, where you have a wide range of photon energies?
Funnily enough, the thing that just got submitted to Nature Materials actually includes using a xenon lamp. So we actually already have incorporated methods to use these like solar spectrums or anything like that. That's already incorporated and ready to go. But for these images, I just used a pulse because it makes, I think, more sense to most people.
Sure, makes sense. And that you're still able to use the same like thermalization models and everything, even when you're exciting at a wider range of wavelengths.
Yes, because so if you treat, basically how we treat these wide range of wavelengths is we say, okay, we basically take your lamp source and break it down into bands of certain finite frequencies and say, okay, we have this many photons per time step of this frequency, et cetera, et cetera. And so this in total builds up this one mass excitation.
Gotcha, makes sense. Other audience questions? We do have a couple minutes still.
So when you subtract out the thermalization from the reference, then the plot that you were showing about the electron-hole pair distribution.
Yes.
In principle, some part of it can be negative.
Yes.
So how do you interpret that as a probability or a probability density?
So the negative part, as in if you're referring to like this here.
Right.
The negative part of this is the holes. So it's basically the missing electrons that have moved over here.
I see. So that will be the hole density, and
yes.
the other
So
one will
the
be
negative part is the hole density, and the positive part is the electron density.
Thank you.
Last call for audience questions.
Very simple question. You were talking about when you supply the density of states at different layers, you interpolate in between. Do you have to be careful about how you do that interpolation at all, and like what method do you use for that I've done a lot of interpolation. It's always trickier than you want it to be.
Yes, you absolutely do. I mean, the biggest and the most difficult part, I think, of that interpolation is caring about how well resolved the density of states that you've provided it are. So really, I would recommend that if you're going to use a method like this, you need enough densities of states in that folder to go all the way from surface to bulk, like every atomic layer. With that, then it becomes reasonably simple, and the interpolation, all it's really doing is saying, okay, my grid point happens to be actually halfway between two atoms, but the difference in densities of states is so similar at that point that it doesn't really matter too much. If you space that out to save yourself some DFT calculations, then you get some really funky looking densities of states.
All right. Any last questions? If not, I'll invite Weishi to come up and get set up, and we can thank the speaker one more time. Is our next speaker here? Oh, yes, great.
Okay.
Without further ado, we'll carry on here, and our next speaker is Wei-Shi Wang, who will tell us about QuickBox v0.6, basis design for electronic structure and beyond.
Okay, hello everyone. My name is Wei-Shi Wang. I'm a PhD student in the Department of Physics and Astronomy at Dartmouth College. Today I'm very happy to talk about some progress of a very I would say, unpopular and small package I've developed in the past few years. It's called QuickBox. And my title is QuickBox 0.6, basis set design for electron structure and beyond. So I think my talk will basically organize into 3 parts. I will try to answer 3 questions. The first question is that, okay, why did we develop QuickBox? So to answer that, we need to ask more questions. That's how you do scientists, right? First, why do we care about basis set? And then what can the previous version, QuickBox 0.5, do or cannot do? And the second part is the meat of the talk, which is what's new in QuickBox 0.6. So specifically, I will talk about 3 main parts: new parameterization system, new basis construction system, and new computation pipeline. And the last part, I would like to ask this question: what is QuickBox if not a basis set generator? So typically, when you ask what is something if not something, you are saying it's definitely only that thing. But here I want to take it literally. So to answer this question, I hope that I can show that maybe QuickBox is not only useful for basis set design. Maybe it can be useful for some other, I think, scientists for some other purpose. And why that can happen, I will explain later. Okay, so I think since I'm in computational chemistry and material science, I don't need to explain too much about this. So basically, the subject of problem we're studying is electronic structure, and we have some electronic Hamiltonians. It's written in the first quantization, and then you will do basis set discretization to discretize to get those like one-body integrals and two-body integrals. And then, so here, when we actually discredit it, we assume that normally we assume it's orthonormal orbitals. And then those orbitals can also be linear combinations of what we call basis functions. And those basis functions need not to be orthonormal with each other, so they will have some what is called an overlap matrix. And then after you discretize your Hamiltonian, and then you can have some eigenstate approximation. We know that the most basic one is the mean field approximation, like Hartree-Fock. And after that, we can apply other, more advanced algorithms. And then when you have some ansatz, you still need to solve them, right? So there are different ways to solve them. But if we look at this pipeline from a basis set researcher perspective, I would say that the really quantified problem that we're trying to study is actually a coupled one. Is what we study is always not entirely what nature provides us with, is actually under this discretization of basis set. So if we look at that, we can see that basis set is actually not only just a preprocess, but it also is an encoding method. It can actually both affect how we describe the target Hamiltonian, and also it might also affect the downstream accuracy or like complexity for the eigensolver. So here, basically, basis set can encode the information, and it can also affect the performance. So okay, so I personally am also from a quantum info perspective. So one thing we really care about is that, okay, can we simulate molecular materials on quantum computers? So we know that in traditional computational chemistry, you will have very accurate method nowadays with either DFT or couple cluster. But when you look at those quantum algorithms, okay, one thing I noticed that, okay, why are people just using SU3G? For any people who, do quantum chemistry, traditionally you will know that it's giving you not very accurate result, right? So it turned out that the reason for that is because our quantum devices are still very limited. Specifically, the number of qubits or high fidelity qubits on your quantum device is directly related to the size of your basis set. So as long as you go to a little bit larger basis set, then it will surpass the limit of your quantum device. So can we design or configure basis set for NISQ molecular simulation in a more systematic fashion? So NISQ here stands for Noisy Intermediate Scale Quantum. So it's the current state of our quantum device. So to kind of like embark on this journey, we basically started this idea to develop a package, which is the QuickBox, and we also kind of like publish a technical paper about it back in 2023. So what does QuickBox do? Or how can it actually help you design basic set? So basically, we're going for a multi-level construction procedure. So we know that for molecular system, typically we would use Gaussian type orbitals. The most simple case is the primitive Gaussian type orbitals. So you just have n here is the normalization constant, and then you have your Cartesian representation of your angular momentum part, and then you have the Gaussian to represent your radial part, right? And then secondly, you can do contraction because we know we have nuclear cusp and electron-electron cusp, and then you need actually the Slater type orbital to describe them. So in order to mitigate that, we basically try to do this multi-concentric linear combinations of Gaussian type orbitals. And then the third level is that, okay, we can basically even take some mixture of different contracted Gaussian type orbital. So on this level, it's basically on the same level of our molecular orbitals in a traditional sense, right? So when we do a Hartree-Fock calculation, we basically do orbital rotations, and then we'll mix different basic functions with different subshells, right? I would argue that maybe a little bit different here is that in a traditional electronic structure calculation, you always go full subshell, right? Because due to the iterative nature of your molecular integral calculation, you might as well just store all the angular momentums. But, okay, so all of those QuickBox can do previously also, so what we add to that, like what new do we bring to the menu? So it's basically this level 4. It's called hidden layer mixed contracted Gaussian type orbitals. So we know that those Gaussian type orbitals, they have their parameters, right? Like the contraction coefficients, the exponent coefficients. Normally we calculate those based on atomic systems or some other methods, and then we just store them or reuse them every time. But we're thinking that what if we can actually optimize those parameters? That would still be too many of them, right? Because you can have in order to have a high quality beta set, you will have so many basis functions, then that would be very costly. And for example, for exponent coefficients, they are nonlinear coefficients. That would be very hard to optimize them. So we need to find a way to be able to optimize those parameters while reducing the dimension of a parameter space. So we do that by introducing some hidden layer to correlate those parameters. So specifically, we have those what is called the primitive parameters, and then they can correlate with each other and then form what is called the contracted Gaussian type orbital parameters, and now they will form like basically a basis function, a basis set parameter. Okay, so this is basically a complete like electron structure computation graph when we're incorporating the construction of your basis set. So on the left part is basically you have some theta here. They are primitive basis set parameters, and then they can couple in some way and then become your orbital parameters, which are represented in P. And then you can use those parameters to build your contracted Gaussian type orbitals. And then you can further mix them to form your mixed contracted Gaussian type orbitals. And only then you have your basic basis set. But then different from the traditional sense, you have track of all those parameters. And then when you feed them into your whatever SCF algorithm or other algorithm to solve for example, ground state energy, you will be able to see the correlation between those parameters along with the coefficients of your eigensolver. So, and then we basically deploy this variational parameter optimization procedure, which is, okay, when we start with some fixed set of parameter values, and then we, for example, here I'm showing you just the simplest Hartree-Fock SCF solver, and then we solve it, and then we add a stationary point. At that point, we try to calculate the gradients of those parameters at that stationary point. And then we update our parameters, and then we do another round. So this iterative back and forth variational optimization actually has shown in the paper of our paper that can actually drastically improve some performance. Okay, so that's basically a recap of 0.5 if you're not familiar with the library. So what's new in 0.6? Okay, so if we look at 0.5's beta set system, basically we take the central idea of Gaussian type orbitals, and then we go two directions. One, we can basically have more ways to combine those Gaussian type orbitals, or the other way is that we can basically have finer control of the parameters living inside of those basis functions. So 0.6 also take further of those two directions. For the construction of your basis functions, we have updated basis construction system. Specifically, we can actually have what is called composable basic function operators. So basically, we can treat some basic functions as value elemental types, and then we can combine them together basically through an algebraic way. So for example, one example of that later on I'll show is basically how you can combine, radial part like the Gaussian with some other part. And then we have linear combinations of mixed type basis functions. That means that, okay, in 0.6, if you want to go crazy, you say like, I don't want to just study Gaussian type orbitals, you can technically define your own customized basis function. And then you can combine that with Gaussian type orbitals. And then at last, we also implement this automatic orbital renormalization because they represent, single particle wave function. We want them to be normalized, and then the more complicated species you have for your basic function, it's harder to, have a, formula to automatically renormalize them. So we actually do that basically based on machinery. And then for the parameter side, we also have updated parameterization. So previously, I showed that we can have those correlations between those parameters, but that's limited to scalar and scalar correlation. But here, we can actually allow array type parameters. So we basically allow, you can have a parameter that themselves is basically an array or vector. And then you can have tensor to tensor correlations. And then the one last thing I think is very interesting is called this dynamic graph connection. And I will talk about it later. So here, we actually try to show a demonstration of what I mean by array type parameter. So this is what I explained before. Whenever you have a parameter, those correlations, you can think of, and when they are basically inside of your computation graph, the parameter themselves, they're actually already forming a computation graph. And in machine learning community, they basically call this directly acyclic graphs. So essentially, what we're here doing is basically building those kind of graphs. So here is basically a new example in 0.6. Now you can have a primitive or starting nodes like the x1 and y1. x1 is a scalar, and y1 is a vector. But then you can actually combine them together. So whenever you construct the x3, it's not just you are calculating the result value of x3. You are actually storing the whole information of this graph. So how is this done on a coding interface level? So here's a code snippet. Okay, you can use QuickBox, and then you can define some. As you can see here, f1 is some mapping function. F2 is a mapping function. Those are just generic, function. It can be, from generic function or anonymous functions. And then you can define a first node. What we use here is a function called gen tensor. So after you do that, you actually get this node x1 here. And then you can see that here is actually of type unit var. And then there's this kind of a double direction arrow here. It means that it basically is almost as if it's a primitive parameters. It has no dependency, and then it stores a value of 2.0. And then, but when you try to construct your x2 here, you actually use another constructor called gen cell param. And then it will give you a reduced param that only have one direction. So this means that itself is only just a mapping of its input to some output value. And here, because everything is stored, we're storing the structure of your computation graph instead of actually doing the calculation, so you can think of it as a lazy operation. So it actually does not, print out the result. You only get to know the result when you evaluate later. So you can do this iteratively, and then you basically get your result at x3. And then when you evaluate the x3 result, you basically just call it as if it's a function without any argument. And then you just get to evaluate the whole computation graph. It's just that easy. And then here I basically verify that, okay, compare the result of evaluating x3 with actually explicitly writing down those functions and then do this computation yourself. They actually match. And then the amazing part about this is that this graph, because it's constructed compositively, so basically each part of it is themselves a computational graph. It can be as simple as just a node or some subsequent stuff. So for example, for the 2.0 here, you can basically replace it with your x1 here, and then treat it as a function, and it will still basically evaluate x1's value and input that. Okay. this part, I would say, is still pretty, I think, similar to, just traditional computation graph you constructed. But here, I think is one thing that actually makes it more interesting is what we call a dynamic graph connectivity. So if you really think about the graph structure, I would consider there are mainly three kind of connection. So there's this one level is that if we consider x2, it's basically like a passing node. It has some input and it has some output. And then you have another level is that x2 becomes like just x1. It's just itself. It's a parameter. And then it provides some pre-stored value. And another one is that basically this x2 can no longer even change. It's basically just like a constant holder. It's like a cache. So in QuickBox, basically it allows you to have those three levels for each node you constructed when you try to construct a parameter. So like an example here is that if we examine the screen level of x1, it's just 1 because it's basically at the beginning of your computation graph, and then it only feeds forward its value. So you can actually use this function setVal to change its value. And then after you change the value, you evaluate x3, which is the end node of your graph, the value will just dynamically change. So this means that you can dynamically change your graph. But what's more is that you can even now, okay, say if I want to change maybe some other stuff. Here is a typo. For example, I want to change x2, but it says like you cannot change it. The reason for that is because if you investigate the screen level of your x2, which here is a typo of x3, it will say that the screen level of it is 0. It means that itself is not some variable. It's really just a mapping relationship for its previous node. So how can you just directly assign a value to it, right? You cannot do that. But what you can do in QuickBox is that you can set screen level. So basically, you can forcefully change x2 from just a simple mapping from its previous nodes to as if it's an independent value itself. And after you do that, you can basically set its value. And then it will also affect downstream graphs. So that means that even after you create a graph, you can dynamically change the connectivity of your graph and change the value of it. And then I would say this kind of inspires some very interesting use case for QuickBox. There's also new custom basis customization system. So if we go back to this previous very rudimentary example, this primitive Gaussian type orbitals, you can already see that it actually made of multiple parts, right? It has radial parts and it also has the angular momentum part. So you can basically consider this as some very primitive function, core function. For example, here is just a Gaussian function. And then you apply some operator to it to actually modify it, to build a more composite basis function out of it. So by doing that, you can actually, QuickBox actually allows the user to define their own core functions and apply some specific predefined operators in QuickBox to construct new basis function. So one example for that is basically, for example, if you don't want to use Gaussian type orbitals, you just want to use Slater type orbitals, right? Now you just swap out the Gaussian function for the radial part and replace it with exponential, and then you still keep the angular momentum part, and then you can basically construct a Slater type orbital for yourself. And one example here I showed is basically we try to do a basis function like flavor of mimicking the one-dimensional Coulomb interaction. We know we cannot have analytical result for calculate a one-dimensional Coulomb integral, but we can actually use sums of Gaussians to actually approximate that. So here I construct just a user-defined function is a Gauss Coulomb. And then I can basically take the linear combinations of them, and then that will give me better approximation of this 1/r operator. But because even though it's 1/r approximation in one dimension, but it actually takes in the position of 2 coordinates, right? So if you look at this operator itself, it's almost as if itself is a 2-dimensional basis function, because it takes the x1, x2. And then in QuickBox 0.6, you can literally treat this operator as if it's a basis function. And then here I can even calculate its overlap. So this is basically the powerful kind of I would say combination between parameterization system and the basis construction system is that you can not only design your custom basis functions, but you can also just treat them as, just evaluate them. So you see okay, now we are doing a lot of custom stuff. But if we want to do realistic calculation, then what's the performance, right? We need to find a kind of like a manageable way to deal with this. So I admit that when I tried to develop those like features, I got a little bit taken away. So I really kind of got a headache to think about how can I deal with all of those. Thank you. So basically, what I do is that we have a new computation pipeline. So in order to do this, we have what is called a computation graph transpilation framework. So you start with what is called the param box framework. So in the previous example, when I show all those different parameters, and then you can couple them to form this computation graph, they're all considered parameter box. And then use those parameters, you can actually construct some field functions. The field functions, they basically take in some Cartesian coordinates, but they are not necessarily orbital because they might not be normalized. So you take them into the third step, which you actually confine them to be orbital, to be normalized, and then you kind of go backwards a little bit because for the orbital, we just want to represent what's the information stored at. But when you actually try to calculate the integral with them, some basis function or orbitals, they have analytical formula, right? So you can just basically, if they're just Gaussian type orbital, you can just use those very mature molecular integral like algorithms. But what if they're not? Then you only can fall back to numerical integration. When you do numerical integration on those basis functions, you would need to make them just seem like generic functions. Because that's how we do numerical function anyway, right? You put in some integrand, and then you try to do the stuff. So this is basically what the step 4 going through this computation graph means, is that when you have an orbital, not only we can construct some orbitals, we can also deconstruct or decompose an orbital and then transpile them into a generic function. And then just this generic function, if you have analytical solution to calculate integral with them, fine. If not, then we just plug them into numerical engine. And so far, we basically use this H-cubature adaptive quadrature engine for the integral calculation. Okay, so at this point, I basically show all the main features of QuickBox. So we can finally arrive at the last question. So what is QuickBox if not a basis set generator? Okay, so yeah, as you can see, I use a lot of green here because I'm from Dartmouth, but I use different shade greens as well, right? So if we look at the left side here, if I do this yellow circle here, you can see this part. If you just focus yourself on this left side and ignore the right side, this is pretty generic, right? It's almost as if it's not really related to any, electron structure or basis set stuff. It's basically just I have some way to construct a very dynamic, graphs, directed graph structure, and then I can basically make some generic function out of it. So basically, what I realized is that after I have this system, maybe I can do something interesting with just this part beyond basis set. So here's one example. So we talk about we have doing some electronic structure solver. One very rudimentary one is SCF solver for restricted Hartree-Fock. What if we just run a differential Hartree-Fock and then we're not using those for example DIIS solvers, right? So this is an example. So we first use QuickBox, of course, we need to calculate the necessary integrals of a target system. So forgive me for using hydrogen as a very simplistic example. I'm just trying to demonstrate, right? Okay, so here I'm calculating the overlap and then autonormalization matrix and the one-body integrals, two-body integrals. And then, okay, here is basically, it's same as the example I showed before to construct a commutation graph, except this is just more particular. We're actually constructing the commutation graph of your restricted Hartree-Fock. And then here I'm basically just following literature here, but I just need to write a few lines of code as if your Hartree-Fock energy is some objective function. And then the result is basically another param box, is a parameter box, but itself, whenever you evaluate it, it will return the value of your Hartree-Fock energy with respect to the pre-stored coefficients. But here, another very interesting function is called param graph caller. So this basically is the transpilation process I mentioned before. It will basically transpile this parameter box into a generic function. And then you can even investigate the parameter of this generic function. It's basically stored in this property source, and then you can obtain to get the value of it. And then here, I'm actually working with like other libraries. So it's not like QuickBox is trying to do everything. You just get a very generic function, and then you can try to use other optimization, very mature optimization or auto-diff like libraries. So here I'm using Zygote and Optim. So use Zygote to get the gradient, and then use Optim as the optimizer. And then I even apply this quasi-Newton LBFGS method. And then you basically just optimize it, and then you can basically get a result. And here, this last to the second part, basically, after you get a result, you can reuse this set val function to update it. And then at last, because QuickBox still has the traditional SCVI hard-to-find methods, you can basically compare results, and they are consistent. So that's I think very related to still pretty related to our kind of like field, which is hard-to-find solving. Now, since I'm already treating hard-to-find as a generic objective function, then what about I go even a little bit further away? If I just use it for a machine learning task. So here is basically a very simple example of training a multi-layer perceptron. So I'm literally following, because the other day I was like scanning through some machine learning libraries in Julia, and I found that this very popular Lux library, they have this example of fitting a polynomial using a multi-layer perceptron. So basically, this is the result. They have just a 3-layer structure, and then they get a very good result fitting a quadratic function. So we can do the same thing in QuickBox. So basically, still, I construct a computation graph using those parameters, and then I basically compile them back to some function, and I can train them. And here's the result. We got almost the same. Like, I would say, not the perfect fitting, but at least it's doing its job. So conclusions, okay. QuickBox 0.6 is definitely a much more flexible basis set design toolkit than 0.5 in terms of customizing basis functions and parameterizing them. But 0.6 is also more than a basis set design toolkit. It could be a prototyping toolkit for numerical modeling. The reason I say prototyping is because I'm not mentioning, a very large scale, millions of parameters, because that will require, parameterizations like GPU or like distributed computing. So far, it's just all done on your laptop. It's just for prototyping. It's really for idea exploring. So potential improvement, so better compatibility with parallel computation paradigms and more intelligent decomposition for the integrals, because now you're dealing so many different kinds of basis functions. And then better support with AD, so far only support like Zygote. And also, of course, better integration with other Julia material simulation libraries. I hope so. So finally, acknowledgement. I work closely with my groupmates, Casey Doodle, who's also in the audience. He also gave a talk in the Quantum Mini Symposium yesterday, about actually applying QuickBox to study what is called a type of basis function, Gausslates, for like electronic structure. So check it out. And also I will thank my supervisor, James Daniel Whitfield, who's very supportive of me like doing this very convoluted basis set study, and of course, all the members of Whitfield Group and all the funding. So thank you for your time.
Thank you so much, Wei-Shi. Since I know we have lightning talks next, Ray, maybe you want to come set up, and we do have time for maybe 1 or 2 quick questions from the audience.
Hi. Have you considered integrating with the Julia symbolics?
Okay, very good question. Okay, so if you look at, if I remember correctly, if you check the commit history of QuickBox, back in early 2020s, I tried to use symbolics, but I think at that time era, it was a little bit buggy. So you can see a lot of this code, like the structure of it is a very symbolic like feeling, right? So basically what I end up having is a system that's both symbolic and numerical. So I think maybe in the future I will consider, but for now, like I want to everything like as less dependent on many libraries as possible. Yeah.
Thank you.
You emphasized how the functionality you've introduced is kind of generic to many numerical problems. Have you considered just breaking out that part as like a lower level package,
yes,
so that people can use it without having to get all
Yes.
of, okay.
I'm actually thinking about just separating the parameterization system, because now it's like so standalone. But I'm just a PhD student after all. I might need to finish my thesis, and whatever comes after that, I will think about it. Thank you.
Anything else? Right. Let's thank the
Thank you.
speaker again. All right, and next we have one of our other fearless co-organizers of this mini symposium, Ray Yang, who, if I remember correctly, is going to talk to us about Freebird, and I don't remember the subtitle, an extensible toolbox for surface free energy calculation via nested sampling and beyond. All right, take it away, Ray.
Thank you very much. Today I'll give you a quick overview of the package we're building at the Wexler Group at Washington University in St. Louis for simulating surface systems. If you're looking at this picture, you maybe get really confused and not sure what's actually happening. That's exactly the point. So we care about the surface at the so-called operando conditions, which conditions changes and the surface react, interact, and reconstruct all kind of complex things going on, and which is really hard to measure and also really hard to simulate. Fairly recently, we published this proof of concept work using nested sampling to study this coverage temperature phase diagram of a simple Lennard-Jones solid with 111 facets. So what we typically do is we sample microstates and we construct a partition function. From the partition function, we can calculate thermodynamic properties such as heat capacity. From there, we determine the phase boundaries and then we draw a phase diagram. As you can see here, for this simple, a free adsorbate condensing on top of a solid surface, we can have a gas as temperature lowered, and then they become disordered adsorbates, and as temperature further lowered, another phase transition happens, they become ordered adsorbates. And then we can also calculate other observables and other parameters. So we've done this with nested sampling, which is a fairly novel methodology, and we want to compare how it works with other sampling methods. And then we just thought about, why not just building a toolbox for doing all kinds of samplings, and also to kind of extend it to in terms of what kind of system we can handle and what kind of energy evaluation scheme that we want to use. So basically, Freebird is a really, really modular code. We had too many modules probably, but it's really intended to leave rooms for further extension and expansion. And we want to use calculators such like a simple pairwise interatomic potentials. We want to also use model Hamiltonians, and also we want to integrate that very popular, very powerful machine learned interatomic potentials. And currently we can handle atomic systems and molecular, in a continuum, so non-discretized system. But we also build a lattice, which I will show later. And here are kind of two examples of what the kind of type system you will encounter in Freebird. Basically, we have a system that spans both horizontally and vertically. What I mean by that is you have your typical set of structs or types to dispatch and specialize your functions. And then we also have this type system to just embed and embed and embed. And it's like layer by layer. It's more like this nested system that kind of similar to the Smoky package. It's really allows us to do some really fast prototyping, experimenting with new methods, with still just a few core functions, to optimize and to retain the performance. Here I will quickly do some showcasing of what system that can be currently modeled with Freebird. At this stage, many of the models are still kind of a proof of concept or coarse grain. It depends on how you perceive them. So here is a very, very simple system. It's just 6 particles in a cubic box interacting through a very simple Lennard-Jones potential. And in this figure, you see the plots of the heat capacity versus the temperature. calculated from 3 different sampling methods. The blue one is the nested sampling, and the orange dots are the classical metropolis Monte Carlo done at different temperatures, and also the grain trace computed through the one Landau sampling. If you look at the code, the top one is kind of prepared for nested sampling, which needs a set of configurations. And then we wrap the configuration, which is actually from the atom space object into a atom worker, and we wrap the workers into a workers project. And then pass them into different sampling methods. And again, we intentionally try to keep everything wrapped in the struct, and then with a lot of default values just for the easy usage for users. And then here are the 3 lines to run 3 different samplings and then get different results. I had to mention that these 3 sampling schemes behave very differently. For this particular calculation, nested sampling probably takes a minute. And for the MC, that each data point probably takes a few minutes. And for one Landau, it's fairly challenging to run for this system, even with 6 particles. Basically, you're sampling like infinite energy levels, and it's kind of known to be challenging. But this will change once I get to the lattice part. Again, we can handle more than a single component. We can basically do as many components as you want. You just define the interactions between each component, and then again send them into this Lennard-Jones parameter struct. Very similar to the previous example, and we run the 3 different sampling schemes. And you can see that all of them agree fairly well. And then comes down to the surface system we actually really care. Again, that's the same example I showed from the second slide. We have 3 particles. First, I condense onto a surface. That's where you see the first very broad peak at higher temperature. And then there's a entropy-driven ordering transitions occurring at a lower temperature. Again, all 3 sampling methods agree fairly well. And here you can see that we actually read in a XYZ file instead of generating our own initial starting structures. So that's a functionality we have. Now, let's talk about lattice system. Embarrassingly, we built our own lattice system. We probably should just use the lattice utilities. But it's something that we want to keep it lightweight and just snappy. So we built a really, really simple parameterized type that the geometry and the number of components are the 2 parameters of this type. And also we build in some very nice visual, just you can see directly from your repo. And this lattice is supposed to be interacting through a so-called classical Hamiltonian that in this example, it takes nth nearest neighbor interaction energies. This can be obviously generalized to do other models, at Ising models, and then just you define your interaction scheme. Here are the examples. And again, we run 3 sampling plus exact. What is exact? It's basically just enumerate all the possible configurations. From there, you will be able to construct your exact partition function. Same story, all sampling methods agree with each other and agree with exact. And on the left, you have just a 2D, a single layer with 4 particles moving around. If you give it 2 more layers, it recovers this condensation behavior and then this ordering. So then we also confirm, this kind of universal physics of this adsorption process. All right, to quickly conclude, what we really want to build is a platform, and we leave a lot of room and space for further expansion and extension. And also we are able to confirm, let's say, the universal physics behind the surface phenomena. And it is actually a high-performance package, and we're able to run it on the NERSC supercomputers using a node, at least fairly efficiently. Lastly, I want to acknowledge the people who contributed to the group, and PI Dr. Wexler and grad student Junchi and undergrad student Douglas, and our serial collaborator Livia from Warwick. And I said for funding, Julia Mosim for the support, because I asked a lot of questions there, and also demand features. And also we got quite a bit of computing resources to try on. And the code is available there on GitHub, and thank you for your attention.
Great. All right, we are just about at time, but I know for a fact that Ray will be around, so if folks have questions, please catch him afterwards. And I think Jonathan is, oh, there, you're right there. Go ahead and come on and set up. So we have next another lightning talk featuring some great thermodynamic ideas, I think, unless the title has changed too much.
No, it is.
Excellent, excellent. So our next talk is from Jonathan Salmeron Hernandez on liquid crystal modeling, thermodynamics, and numerical methods. And hopefully it will be up here in just a moment. Wonderful. Take it away.
Yeah, all right. Hi, everyone. My name is Jonathan. It's a great pleasure to be here. I'm actually currently I'm a postdoc at New York University, but most of the work I'm going to present was performed during my PhD studies at the University of Chicago under the advisement of Professor Juan de Pablo. So pretty much I'm going to introduce you to liquid crystal GLBT. I'm going to let you know what these letters stand for later, but it's pretty much to model liquid crystals, and I hope you will find it very entertaining. First of all, what are liquid crystals? Okay, liquid crystals are a state of matter that you can find everywhere. So it's not like a very magical stuff. Like it's pretty much something that is in between a solid and a liquid, right? So for instance, like a solid has very well perfect aligned orientation. However, liquids are very more like random, like normal water. So liquid crystals are something in between. As you can see in the image, I hope everyone watched Finding Nemo because it's one of my favorite movies. But in that movie, we can see that when fish as directions, they actually flow naturally like any other liquid, but also have some degree of orientation when they point into an arrow. So this is actually a liquid crystal state, but we can also find it in some other instances, like most of you have a liver and hope, and that is actually a living liquid crystal because the cells can flow but have orientation. And also, we have other technologies like LCD screens, which stands for liquid crystal display. And also cell membranes because they have orientation, but also flow. So these are liquid crystals, they're everywhere, and most of the examples that I'm gonna show, I compared with actual experiments. All of them are liquid crystals, so don't think of them like something strange. All right, so how do I actually model? I actually model liquid crystals with a mathematical approach. First, I need two things. First, the first thing is a vector, which tells us the direction of the liquid crystal. So they're pointing in average in one specific direction. Secondly, I need a number, which is the order parameter. So it tells me how ordered the liquid crystal is. If it's 0, it's pretty much like a normal water, but if it's 1, it's almost a perfect crystal. So with these two entities, I multiply the director vector, and then I get a matrix or also a tensor, right? This is actually the information, the Q tensor is the actual mathematical entity that contains all the information about the liquid crystals. So this is actually the thing that I need to evolve in time to actually achieve my simulations. So most of the current research is done by actually solving that differential equation, which is the Veris-Edward equation. However, that equation has a problem, which is that is clearly missing a concentration dependence. As I don't know, if you're a cook, if you like to cook or not, I hate cooking, but I think when you have to bake something, you need to know the amount of ingredients, like how many eggs, how much milk, how many other flours. So actually concentration, the quantity that we need to have to actually achieve the experiment and to actually produce new technologies is actually important. So most of my research is actually deriving how do we integrate into the Veris-Edward equation the concentration component as a dynamical variable. Unfortunately, I don't really have time to go through this equation or the derivation, but I will let you know how to find it later. But we pretty much use thermodynamics or non-equilibrium thermodynamics through a generic framework. That's the G, like at the beginning of my the name of my code is G of generic. So that's the generic framework, and all these equations actually The two first equations actually are used to model the flow or the velocity of the fluid or the velocity of the liquid. The third equation is, you can see there, is a phi. It's a phi evolving in time. So that's actually how the liquid crystal concentration is going to change on time because of the diffusion process. The fourth equation is a generalized version of the other equations, how the Q tensor or the order is going to evolve in time. As you can see, I have split into energy and entropy. All right, but so the problem with that is like I have a bunch of differential equations, right? But I have a Q tensor, or I have a tensor, I have a matrix that I need to evolve in time. So most of the package that we can find in Julia are actually usually thought to evolve scalars, just a number. So I actually need to change the architecture of differential equations, that GL, to be able to use my Q tensor. So I need to define first the structs. As you can see there, I've defined the structs. The first is the phi, which is the concentration. The second is the Q tensor, which is the liquid crystal information that has some mathematical properties. And the third is the F, which is for velocity. Then after that, I use a central difference because I have partial derivatives. I have a spatial derivatives that I need to actually change, discretize over space. And this is how it looks like. I put different tags for different operators, such as Laplacian, divergence, gradient. All of I hope that you might be familiar with these concepts. And then this is how it looks like in the computational implementation. But something that I want to point out is that it's used for Laplacian, that it's in any kind of number. It could be a float, it could be a vector, it could be a matrix, it could be an array. So that's the difference that we did, the changes that we made. So we did the integration with finite differences, the JL. And something that I think over this conference, something that everyone is pointing or everyone is highlighting is that we want to see the equations that we write it in paper as we actually see it in the computer. So it's exactly the same situation. I have different energies or entropies. And I hope that everyone can see that I have a Laplacian there operating over phi. And then I have this operator, which is the Laplacian there, operating, and I had the result in my multiplication. Similarly, if you add all these different energies, we have a mu, which is the chemical potential, and then we also have, again, another Laplacian operator of a chemical potential. With that, we just simply use the same technology as the differential equation JL, and then we are able to evolve in time this particular setup that you have seen probably everywhere. How does it look like? Well, that's for the concentration, but how does it look like when we evolve the Q tensor? So this is a three-dimensional simulation, and then this simulation was done by Suraj, who is a PhD student in my group, and he is the first acolyte of this package, and he was trying to understand what happens to the liquid crystal when we apply electric field. And the results are very neat. As you can see here, we start to form different patterns over three-dimensional space, which resembles quite nicely like the experimental information that we see here. He also added tensor operators JL because to handle the complex tensor multiplications. Next, what happens if we actually couple the Q tensor with the phi dynamics? Here I am introducing another experiment, which is actually liquid crystal droplets. You see that they are different, right? Instead of being spherical, they are more triangular. But also in the same way, we start with the spherical droplets and we evolve on time, and we also capable of achieving experimental results. The simulations look also like experimental results. We also can add flow, as for instance here I have a liquid crystal droplet that is moving in a channel, right, under a parabolic flow, but also my simulations also can resemble under a parabolic flow these experimental features. However, something that is probably more of interest of everyone is like that velocity that I just showed has a constant velocity profile, but what happens if we actually want to add a flow that is chaotic? For instance, in a liquid crystal microtubule experiment that is based on proteins, these proteins actually transform the chemical energy into mechanical work, right? Because they have, the glucose, all that we eat, and then when we put it outside a Petri box, we achieve a liquid crystal nematic phase that is also chaotic or is active because it's moving just because it has energy. Also, obviously, we couple the Q tensor with the velocity profile or the Navier-Stokes equation. We also achieve a similar result like we see in the experiment. We achieve this, and that's the reason I have LB, because with the lattice-Boltzmann method, which is just an algorithm that was found in Trixie.jl, which is the T in my liquid crystal GLBT. These people had already handled all these numerical methods, and they were very nice to also help us to integrate or find the differences with the final elements, customize, and then couple all the equations together. Finally, which is probably more of interest, is like when we couple the 4 differential equations together, we achieve a numerical simulation that it tells us how ordered it is, how much it is, and how fast it goes. And this is actually to the best of my knowledge, the very first ever active allotropic or concentration-dependent liquid crystal simulation, because as you could see, it was very hard to integrate all the differential equations all together. Which is nice because I hope that this can be used for later applications. So just to sum up, I presented the generic equations, which was based on thermodynamic, non-equilibrium thermodynamics. Then after that, I presented how we solve it with this package that I hope it can be used for other differential equations, not only liquid crystals, other more complex differential equations with the packages that we integrated. And then now that I am here, I saw different packages that I can use for modeling more complex scenarios, such as diet, differential equations estimators, MPI for supercomputing. And I hope that all this helps us to actually probably achieve more complex simulations like artificial muscles, because you can see here that the muscles have like these elongated particles like a liquid crystal. All right, with that, I thank you very much. If you want to know more, please check my thesis. That's how I couple the questions, integrated, derived, everything. Thank you.
All right, thank you very much. Maybe one quick question while the next speaker sets up. So, Chi, if you want to come up and get yourself plugged in here, if there's any quick audience questions. All right. If not, let's try to stay on time. We'll thank the speaker again. I think he'll be around afterwards if anything comes up. So our next speaker is Chi Zhang. We'll be talking about accelerating Fermi operator expansion, ML-inspired methods.
Oh, sorry, how to...
Give it a second, sometimes it's just... Oh, okay, yeah, you just have to... Exactly.
Choose mirror.
You should be able to...
Oh, okay.
That's different,
sorry.
Right?
Let me just...
Yeah,
I
think mirror, yeah. There we go. Okay, wonderful.
Can you see it? Okay. Hi, everyone. My name is Chi Zhang, and today my topic is recursive expansion of the Fermi operator with GPU acceleration. My GitHub handle is Singularity. You may probably have seen it before. So here, first, I will separate my talk into the science part. And so the problem of that we want to solve is to given a Hamiltonian matrix, and we want to apply the Fermi direct function onto it. So in case you forgot what it looks like, it's like this. And then we will obtain the density matrix, and we can use density matrix to do a lot of things. And but what's the problem with this like function application? We need to direct diagonalize of the Hamiltonian, which is like the first line of this code. And then we can calculate the density matrix like this, but we can just, so both of the steps are cubic scaling, but we can ignore the lower lines. It's not important in this part right now. So why do we do this? Why do we calculate rho? Because we want to calculate like energy band, the band energy like trace of the rho times h. If the rho is sparse, this process is linear scaling, which can greatly accelerate our speed. So direct diagonalization is good, but is there any way to avoid it? Of course. So our group in Los Alamos has developed a method like called the recursive application of the second order spectral projection polynomials. So you can see like to approximate step function, you recursively apply these two functions, y squared or 2y minus y squared. You will get something more and more steep. So eventually it will look like a step function, which is the zero temperature approximation of the Fermi direct function. And it does have some benefit. For example, it converts a nonlinear function into a mathmal, so which could be accelerated by GPUs. and it avoids direct diagonalization. But the problem is like it has slow convergence, and also the T range is too narrow. So we have developed a new method called generalized SP2. The formula here may look horrible, but the idea is very simple. For example, we have like 4 by L. L is the number of layers. Matrix. So we have such a matrix, and for each column of the matrix is 4 parameters which define the layer of the model. And for example, for L equals to 3, and we can obtain a polynomial of order 2 to the 3rd order, which is 8. We'll have something like this. So like in 10 steps, we'll have a polynomial of 10 to the 24 order. So if x here is a number, we'll obtain the Fermi-Dirac function onto an eigenvalue, which is a density, fractional occupation. But if the x here is a matrix, like the Hamiltonian, we'll obtain the density matrix. So how to obtain the model? We do it by training, which is we borrow some words from the machine learning, and the training data will be a set of sampling points on an exact Fermi-Dirac function. And we use the LISC-fit.gl package to do that thing. And there is curve fit, which Chris Rebecca has just introduced today. And we'll also plan to use that to speed up the speed of the fitting. So we can fit any function. On the left is a Fermi-Dirac function. On the right is entropy function. And you can see that this one is the SPU old model, and this one is the new model. So on the bottom is the error. It looks like messy, but it doesn't really matter here. So this is the fitting accuracy versus time versus number of layers. As you can see, with enough number of iterations, we'll achieve very good convergence, like 10 to the minus 9 or 10. And this on the right is the time for fitting it. I use different AD backends to accelerate the Jacobian calculations. This is the fitting against different temperature, inverse temperature. So I just want to detect what's the boundary of the inverse temperature that we can use. And this is the GPU accuracy and the performance benchmark. On the left is the norm difference of the density matrix calculated using this method against the benchmark matrix. So I also, on the dashed line is the exact diagonalization, and the solid line is the model GPU. I also test against different input and output precision with different math models, math mode set. On the right is the performance. You can see with the model, we can achieve 10 to 100 times performance against the exact diagonalization for a system size of 16,000. So I also developed a package called InsideCompute.gl, which can calculate the T-flops of the model. So it's like 600 teraflops, which is 1/3 of the maximum which H100 can achieve. So the second part is about software engineering. I'm running out of time, so I'll speed up. So how to design a good API? We can use function like objects, which sometimes we call functors. So the first, it's only because we want to evaluate a model on a number of matrix, so it's very natural to define something like the first 2 lines. But what if I want to apply the model to an array of numbers or matrices? I cannot do this one because model is a matrix and this is a vector. They don't have, their dimensions do not match. So we can define a functor interface like this one, which is just an alias of that function, and we can voila, we can do that thing. And we can also use map because model is kind of a function right now. We do not have used any lambda expressions. So we also use ADs. And this is the manual model, which is the fastest one, but it's an analytical one. So it's kind of lengthy. I also try to use different backends like Enzyme, Mooncake, Zygote. But I don't like it, so because the code is messy, and we finally differential interface comes to save the day, and voila, this is the code, which is very simple. It only has 2 lines. And always benchmark. You use benchmark tools. I also contributed a little bit. And also, there's a new package called Cheermarks. I gave some suggestions to Lilith, and Lilith fixed it very fast. And also, we have used CUDA and also NVTX. And in case you don't know, NVIDIA just published a Copilot extension on VS Code. And we got also, there's other method like keeping types stable, like using 0, 1 unit, and similar stuff. And also, we can reduce allocations to a wide push, and we can reduce the allocation a lot. But why do we make choices? We can keep best of both worlds, right? So we just use Holly trait. We can define a trait and dispatch on both methods. And also, don't add unnecessary type constraints, which this is unnecessary because sometimes I want to do symbolic calculations. I can put a symbol here, and we can use CUDA and BLAS. And next step, we'll be using Rectant. Okay, so we can also use tensor cores by these combinations of input and output, and also math mode and other stuff. So we can use package extensions. So I'm not going to dig into this part. And I've developed some packages during this project. And Inside Compute and Inside System is still working in progress, so your PR is welcome. And thank you, that's it. Okay.
All right, thank you for that whirlwind tour. I love the Gershgorn-Stoker theorem, so great little linear algebra shout out there. Maybe 1 or 2 very quick questions, and I'll have Henry come back up to get set up in the meantime.
So from my understanding, you use polynomials for your fitting because it's like better, it scales better with GPU, right? Mm-hmm. And so is there any advantage to using like or a set of orthogonal polynomials as your basis?
Orthogonal polynomials like other kind of polynomials?
Yeah, like Chebyshev and stuff like that.
Yeah, there's other kind of polynomials, but this one converges the fastest. It's very simple, but the very fastest one, yeah.
And are you, since you actually, your slides have a really nice overview of just Julia in general, are those going to be available as well online?
Oh yeah, it's actually public. I mean, I because it's a Lano project, so we do have some paperwork to do, but I currently make it public for you to see it. I just go to my GitHub and you will see it. Thank you.
Great.
All right, thanks again. And last but certainly not least, I'm happy to welcome Henry Snowden back to the stage to tell us about nqcdynamics.jl, non-adiabatic quantum classical dynamics in Julia. And whenever it decides to come up, the floor is yours.
I hope you've, recovered from my voice from the last time. Right, here we go. So yeah, I'm going to be talking about nqcdynamics.jl, or more importantly, NQCD, a whole repository designed around the idea of non-adiabatic quantum classical dynamics. And this time, unlike last time, this is not a solo operation. I haven't been working for 8 years. So I would just like to thank everyone who has developed on this, both in the past, all overseen by our professor, Reinhard Maurer. Here I am, reasonably near the future, just 2 years into my PhD, and so I thought I would shout out everybody who has worked so hard on this package and all the other packages involved. So what are non-adiabatic effects? Where are they relevant? You may have heard of them in your sort of master's chemistry and physics courses if you did them, otherwise they're probably alien to you. Non-adiabatic processes really occur when we need to treat our electrons and our nuclei on the same sort of timescales and explicitly coupled together. And this really often entails excited states, so if you see things like lasers, linking back to my last talk, then you probably will be involving some level of non-adiabatic effects in your processes. So again, this can include sort of, your photocatalysis and photovoltaics of before, but also deep space science is very heavily driven by non-adiabatic effects. And importantly for the Julia community, all of your quantum gates are also entirely driven by non-adiabatic effects. And so simulating these is incredibly important for understanding any of these more complicated processes that go beyond the most basic of a sort of simple chemistry, shall we say. So what they really entail, as I said, is we have to treat our nuclear and electron dynamics equivalently in time. And what this really means is we can't use our favorite friend, the Born-Oppenheimer approximation. So we have to keep everything coupled the whole way through. And I think this little picture graphic does a pretty good job at representing what that means. In our Born-Oppenheimer picture, we pick nuclei as our electron, and we propagate them in time using some equation of motion, and we either fix the other one or update it sort of systematically throughout, rather than continually. In our non-adiabatic problems, we have to do them both simultaneously and entirely coupled. We can't just update one stepwise, they both have to be systematic. And to show you sort of what a non-adiabatic effect might look like in a chemical system, here we have just a molecule of water on a surface. An electron is going to move from our surface to our molecule, and that's going to force the molecule to hop up back onto its excited state. And then this, obviously, being on its excited state, completely changes how both the nuclei and then the electrons will interact with each other and progress in time. And so we can't really efficiently solve non-adiabatic effects in the atomic simulations of interest at the time and length scales that we care about. And this is obviously because if you were to do this, you're basically solving the full Schrödinger equation for some problem that is not hydrogen. And that would be pretty hard to do. And so what we do is we take the mixed quantum classical approach, which means we do quantum electrons and we do classical nuclei. And this makes everything a lot easier. And just a couple of videos to show you the difference. Here we have classical molecular dynamics, which is what we refer to as Born-Oppenheimer dynamics. We have an NO molecule vibrating. It's going to hit a surface of our gold, and it's going to sort of just bounce off, not really caring, going about its day as it was. Now, in independent electron surface hopping, a very high-level non-adiabatic method, instead what happens, if you watch the electrons over here, when it comes to the surface, all these electrons very quickly excite, and the vibrational mode is quenched. So we've had vibrational energy converted into electronic excitation within the very few femtoseconds of that interaction. And that's really the core of non-adiabatic effects. Electron energy converting to vibrational or nuclear, and vice versa. And as before, I always like to point out some other codes and state of the art. I think it's very valuable to know what's out there. And a few noticeable mentions that have been very successful include Shark, Newton X, PyXade, Jade, and many, many more, honestly. But a lot of these have many problems that led to the development of NQC Dynamics and NQCD around 8 years ago. First of all, ones built in Python can be very slow. We all know Python is very slow. It's an interpreted language. Never use nested for loops. You'll be there all day. Also, they're often built to deal with one problem, either condensed matter non-adiabatic dynamics or molecular non-adiabatic dynamics. They don't breach both, and they often don't include a large array of methods, including electronic friction, surface hopping, Ehrenfest, and many more. And then finally, and a real key thing for me, is that they don't include, or they often include only on-the-fly dynamics, which means an interface to a DFT code, etc., and don't include model Hamiltonians or machine learning integration to really push the bounds of what you can do. And so NQCD is going to resolve all these, and it really has three main design considerations. First and foremost, we want to be able to prototype a method and very easily drive that all the way to production and publication-ready material. We want this to be a seamless and easy workflow. It needs to be high performance, as mixed quantum classical dynamics are often stochastic in nature, and what that means is that every data point I will show will have at least 100 and probably 1,000 calculations, if not more, driven behind it to make it statistically significant. And finally, we want to provide a larger range of electronic structure methods as well as nuclear dynamics methods to provide a great deal, a plethora of different non-adiabatic techniques and simulations that you can perform. And again, I always like to shout out the advantages of Julia, as we definitely want to persuade more and more people to come here and use it. The advantage for our first point is that Julia is a high-level language, which means, again, implementation is easy, very easy to write in, and just-in-time compilation means with very little effort, you can go from something very unperformant and Pythonic to almost C-level speeds. The native parallelization and trivial GPU computing also makes this extension to ensembles of thousands of simulations very simple and trivial. And then finally, multiple dispatch is really a massive friend of NQC dynamics, and I think it would not exist without it, as this ability to just say, okay, my electronic structure is of type X, that means that I propagate it through equation of motion Y without having to change much, is so simple and so powerful and makes this code so efficient. Like I said, that is really all in Julia and the reason behind us here. So NQC Dynamics does all of that, and it had really one more aim for us, which was enhancing reproducibility in this field. We wanted to be able to perform dynamics, publish dynamics, and then allow anybody of interest to go and do the same thing, to check our results, and to maybe extend our workflows. And I wanted to shout out Dr. Watson.jl, a package that, if you're not aware of it, is incredibly powerful in scientific computing for really enhancing reproducibility. And one last quick mention is we have started to incorporate quantum nuclear effects in the idea of ring polymers, and I won't go into any more detail than that, but if you're interested, it is slowly happening. So using the code, we're kind of a surface science group, though we do lots of different things, and so we've really applied the code to gas surface reactions, and that's our interest. And for this talk as a model electron system, I'm going to use something called the Tully Model 2, which has recently been extended to model the photoexcitation of this molecule. And the main idea of this model is it's of an atom or a molecule moving through some level of interface or barrier, and then either reflecting off of it or passing through. This here is the diabatic representation with a diabatic ground state set to 0, an excited state that crosses over, and some coupling terms are off diagonals here. If we rotate this into the adiabatic representation, which is the one most of you will be most comfortable with, if we were to perform Born-Oppenheimer dynamics, this would be just living on A11 and never leaving it. Whereas, due to the close proximity of our excited state here, it's possible to absorb some vibrational energy, hop up, make this quick shift across, and hop back down. And this is a pathway that is only possible through non-adiabatic dynamics or non-adiabatic effects. This is the workflow of NQCD. It's pretty big, and it is pretty scary, but it also does do quite a lot of stuff. But to really break it down, what you have to care about is the electronic model, the dynamics technique of choice, and your atomic structure. Then you need to pick how you would like to sample your initial conditions, and kind of everything else is handled for you in the code. You can access it at any of these points if you do want to modify things, but otherwise you can just let it go. Outputting, obviously, you can output RU, which would be our velocity positions and quantum states, but we can also have some convenience things, including desorption and dissociation probabilities, vibrational rotational states, just to make your lives a lot easier. And for initial conditions, of course, electronic and nuclear, as they're the things we're propagating. And we include both pure and mixed states at finite temperature for our electrons, and thermal atomic sampling via Boltzmann and Wigner distributions. And I believe we're getting slowly towards nested sampling for these things as well, to link back to Freebird, but I think that's all sort of up and coming. So we're going to start with our model, and this is in nqcmodels.jl. There's a theme with our naming, you might notice it. And this is really a massive model library that incorporates everything from model Hamiltonians, neural networks, ab initio dynamics, interfaces through ASE. This is a horrible name, never try and read it, and electronic friction tensor providers in all sorts of frameworks. And the real core message or principle around NQC models is to make it super easy to implement your own model to then perform dynamics upon. As the dynamics methods themselves are pretty rigorous and you don't really want to mess around with them, but what you're modeling, what electronic structure you're modeling, is definitely something that we want the users to have control and be able to plug in any machine learning model that they might have of interest. And to show you this, we're going to make a model here live. First, we're going to define a structure, JuliaCon Tully 2. It's a quantum model because it's going to return a Hamiltonian, and it has some parameters that I've set as default here to make our lives easier. We need to tell it the number of atomic degrees of freedom. Back from the graph, it was a simple 1D model, so only one, and the number of electronic straits that is involved, and here we just have 2. We need a potential function, which is an in-place function that returns some form of Hermitian matrix. And we need a derivative function that returns the derivative of that Hermitian matrix, both on a diabatic basis. And whatever these are, we don't care, as long as this is what you have. And with this, you now have access to the whole suite of NQCD. So this could be a machine learning model interface to a Fortran code that returns these two things. We don't care. As long as they're named this, it will now work with all of the NQCD infrastructure. So just to test it, we're going to define a set of positions. Everything in NQCD uses atomic units, as that's the most convenient and natural units of the problem. And as it's all in place, we're going to define some vectors, and just with a little bit of diagonalization, we get our adiabatic representation back, so we know that our model works and it's what we expect it to be. And that's everything with respect to a model. That's all you really need to do. And so we go on to our dynamics. This is the more interesting thing, I think. So NQC Dynamics.jl is the sort of flagship top package. And it really provides a collection of methods, both from Born-Oppenheimer adiabatic all the way to our non-adiabatic dynamics methods. And it includes things like surface hopping, here fewer switches surface hopping, Ernst, which is the most classical one people may have interacted with before, mapping Hamiltonian methods, and a plethora more, and this is not the entire list, but this was the list we printed in the publication, so that's kind of what you're getting. And as far as we're aware, this is the largest range of methods, especially surface hopping and mapping Hamiltonian methods available, and I believe it is the only publicly available implementation of independent electron surface hopping, which is considered kind of the state of the art. So it is really a thorough library across your options available, and we think the sort of best place to go for non-adiabatic dynamics. So to run our simulation, we're going to take our model, as we had before. We're going to define an atomic structure. As this is a simple 1D model, we just need to give it a weight. That's all it really cares about. And here, this is the weight of a hydrogen atom in atomic units. We need to define our dynamics technique, which is our fewest switches surface hopping that I've briefly mentioned. I'm not going to go into details about what any of the dynamics methods are. There's in all of the documentation, there's all of the equations and derivatives and everything you need to understand it. And we're going to pop all that in a simulation. We're going to define a convenient outputting function, which is going to return the probabilities of transmission and reflection through our little barrier in the adiabatic basis. And we're going to define that every data point will have 500 trajectories and a range of initial momenta, again, in atomic units. And you can use Unitful Atomic, a great package to make using atomic units easy, because I don't know anyone who likes them, honestly. They're pretty awful to work with. So let's run it, loop over the momenta, set up our initial conditions, set up our time span, and we now need to build a distribution. Obviously, this has to be a product distribution between our electronic and nuclear configuration, and we make this super simple for you. All you have to do is define your nuclear configuration, which is just your position and velocities, and the size of the sim just returns the number of degrees of freedom. And if you were to put here objects from statistics.jl, any level of distribution, it would sample from them automatically for you in order to sample a range of initial conditions rather than just individual ones. And our electronic initial condition is going to be a pure state, which means an electron entirely in a single state rather than some mixed. It's going to be in the ground state, denoted by the 1 here, in our adiabatic basis, so in our adiabatic ground state. We're going to run these dynamics using diffeq. So it's very sort of standard diffeq principle, really, with their trajectories and their reduction algorithms. And we're going to push our output as a dictionary to some pre-initialized vector to make our lives a little easier. And with this, we get this weird-looking graph that I will now explain. Basically, what this now shows you is that the reflectance on the ground state is basically non-existent other than this small blip here, which means we very rarely move along our adiabatic state and hit back. Our transmission on our ground state is dominatrix at low momenta as well as very high momenta, and this is basically your adiabatic result. If we were to perform Born-Oppenheimer approximation, this would be 1 across the board, and it just denotes moving along here. But as we increase our momenta slightly, what we then see is we actually see hopping up because we have enough vibrational energy to donate to make this process happen, and then hopping down and moving through that way. And that is what T2 denotes, that second pathway. But obviously, as we increase our momenta to very high degrees, it goes so quickly that no real scattering or interaction can occur because it just flies through our barrier with no real interaction time. And this compares pretty well, or well, exactly to the results by Tully, the developer of the model, back in 1990. So the method works, we've implemented a new model, and we can perform dynamics on it very easily. And everything's set up to make it so that any implementation of new methods or models is as easy as possible. And that's really the aim. But obviously, NQC Dynamics goes much further than this, and I really wanted to show you some of the more insane or interesting things that we've managed to do with the package and have actually led to real publications. As what I've just shown you isn't really publication worthy, as, like I said, Tully did it in 1990. First of all, I'd like to compare our dynamics methods with the hierarchical equation of motion. This is the kind of as expensive as you can go method in this field. This is full quantum nuclear and quantum electrons, but it just traces out the metal states to make everything a bit more manageable, and therefore takes a few approximations on the electronic structure of the metal. And we're going to do this for our NO on gold, which is the videos I showed you at the very beginning were from this data. And here is a lot of data, I will admit. The main things to take away are the bars are experiment, the black lines are the hierarchical equation of motion, and the red lines are our IESH calculations, about 1,000 simulations per data point here. And really, across the board of all sorts of different initial conditions and systems, you can see that IESH matches pretty well with HEOM, and it's a fraction of the cost. Each IESH calculation can be performed on one core in about an hour. A HEOM calculation is multiple nodes on a supercomputer for days. So at a fraction of the cost, you can get pretty close, at least in this system, to a much higher order method with our techniques. And to sort of show you the absurdity that we've managed to go to, using a neural network that's been trained on some constrained DFT data by the Binjiang group in China, we were able to take their complicated diabatic potential energy surfaces that their neural network generates and feed it into our ISH calculations. And then this allowed us to do about 18 nuclear degrees of freedom. And I think I did the maths earlier. It was like 34,000 potential energy surfaces that our electrons could interact with to perform some absolutely insanely expensive and complicated independent electron surface hopping calculations. And this is really much larger than any other simulation that's ever been performed in this field before, or performed through Julia here, thanks to its pretty incredible speed when you optimize it. And again, each of these data points, I think this time is about 10,000 calculations. So the scalability of the problems that both NQC Dynamics and Julia allows you to go to is quite frankly insane, and it's really opening up the ability, along with machine learning, to do insane new in-detailed studies that allow us to really investigate what is happening in more complex systems. And finally, I wanted to link back to my previous talk in lightmatter.jl by incorporating some two-temperature molecular dynamics with electronic friction simulations. And so here we have a two-temperature profile that's been generated from lightmatter.jl at various laser fluences over around 4 picoseconds. If you aren't really sure, refer back to my previous talk. And we use this to parameterize an electron thermostat and a photon thermostat, which allow us to give energy to some hydrogen atoms on the surface, as well as allow our copper atoms to move around. And this is all driven through what, like I said, electronic friction. But a massive, complicated system, many more nuclear degrees of freedom than our previous simulation, but a lot less electronic degrees of freedom. So once again, we have to rely on machine learning to make any of this possible. And I really want to emphasize that complicated chemistry really relies on machine learning these days. Without it, we couldn't do anything as insane as this. And so we use FHAIMS, a DFT package that our group partly develops, along with NQCD, to do some adaptive sampling to train some very accurate machine learning models, not just on energies and forces, but actually machine learning on the dynamical properties of interest, such as desorption and dissociation or sticking probabilities, which is, I believe, never been done before now. And this gives you a molecular dynamics trajectory, which after all this work in machine learning, I will admit is not that interesting. It has some hydrogen atoms moving along the surface, and eventually they meet each other, decide that they'd like to be friends, and leave. Which, you know, I guess hey-ho. And this is all happening as our simulation goes on. Our temperature has followed this profile, and here's the electronic tensor for anyone of interest. And what we really want to do with this is we wanted to compare differences between two different levels of theory, local density friction approximation and time-dependent perturbation theory, and to really get into grips with the difference in how they move energy about, we have performed here, I think it's 250,000 calculations per bar, so absolutely insane levels of calculation using GPUs to really drive all of this. Without them, again, not really possible. And you've noticed that in the last sort of 5 to 10 minutes, I've shown you no code. Luckily, if you want to find the code, we have a repository called nqcrecipes.jl that gives you a tutorial on how to do everything I've just shown you, and to make it easy to pick up and learn any complicated workflows that we may publish in the future. We'll try to keep this up to date with everything we do to make anything of interest that you may see in publications available to yourselves. And this, again, includes how to run NQCD on GPUs or CPUs. And there's the link for it. And so really, to wrap up, I've shown that NQCD is a toolkit of methods for non-adiabatic mixed quantum classical dynamics. And it's just had its largest 1.0 release that we've just pushed through insanely over the last couple of weeks. So thank you, everybody. And that's majorly improved the usability, has also completely reworked the back end to provide much easier to extend to more complicated systems. And we've done all of this somehow without making any breaking changes. And I have no idea how that's happened. And all of this massive 1.0 release has allowed us to do some insane stuff, such as now include correlated electronic Hamiltonians, density matrix propagation directly rather than coefficients, and directly driving our systems with light rather than just taking temperature profiles. And thank you all for your attention. Do you have any questions? Here's QR codes to everything, recipes, and dynamics.
Thank you so much again, Henry. And we do have a few minutes for questions. Anybody?
Right, thanks for the beautiful talk. I just first want to mention that JuliaCon Talito is such a sensational name. And my question is, you touched on the future work, including model Hamiltonians and even the density matrix propagation. These are very expensive operations. And what's the plan to actually execute this part?
Yeah, they are very expensive. So the aim behind it is sort of using GPUs and really relying on them to drive any of the density matrix stuff. So obviously GPU matrix operations are incredibly efficient. And as well with our correlated systems, we're going to be using reasonably simple systems, at least at the starting point, maybe low dimensional Heisenberg models, that sort of thing, as well as abusing tensor networks and what's all going on there with like DMRG, all sorts of different processes there, as well as trying to reintroduce our machine learning, see if we can also machine learn on some of this correlation to make everything nice and efficient.
I've seen some ideas of work on the Holstein model to couple the electrons.
Yes. So interestingly, you bring up the Holstein model because all of them ISH calculations actually use the Holstein model as an absorbate metal bath model. That's how we treat it. So it would definitely be very interesting to sort of nest Holstein models and have Resorbate its own Holstein model in a larger Holstein model that is the bath. Very interesting approach.
Thank you.
Go for it.
Unit. Feels like you have mixed feelings towards unit. Sometimes you use them, sometimes you don't. I kind of torn as well. What's your opinion on that? To me, it's like a passive safety there that you're doing the wrong physics, you will run into errors. But yeah, I share that even a single little bit of overhead, if you strip it down, I can squeeze out a little bit more performance since you're working with such a gigantic model. Very expensive computation.
Yeah, so my opinion on units really is anytime you do anything for the first time, you should absolutely make sure your units are correct. And I do believe all of our packages should implement sort of captures for this, So if we submit units, so if you submit unitful quantities, what the backend will say is, okay, this isn't a flow, it's a unitful quantity, let me convert to the correct units for you. So, and I think this is very important just to make sure people don't accidentally make unit mistakes, which is obviously a very common issue. But I do agree that obviously unit full quantities have a overhead to deal with. And I especially don't think that our dynamic simulations should actually be using units throughout them, as we've seen that is quite a large overhead. And so if you want to use units, it should really be sort of a first point of call, strip the units away, do dynamics with float, and then re-add units at the end if that's something you really want to add. But
I agree. Yeah, carrying along units can catch mistakes, but can also be a pain in the ass. So I think we've probably all experienced that.
Also, some of your functions may not trace through very well with units, and then you have a whole host of problems.
Also, the number of times I've run into things where it's like these are the same unit, but somehow they come out in unitful as to, like, I can read them, and it's like these are clearly the same, but you're like not parsing it correctly.
Any level
or-
of composite unit is absolutely a nightmare.
Yeah.
I tried to implement some fancy automatic unit conversion thing in light matter, and it just became a nightmare because anytime, like, watts to EV per time obviously doesn't work, and so it just all breaks.
Yeah.
Like,
Oh, I feel your pain. And we've had a lot of debates in the Atoms-based crew, like, do we need to require units and all of these sorts of things. Anyway, all right. Well, with that, thank you, Henry, and thank you again to all of our speakers, both in the afternoon session and throughout the day. Let's have one more round of applause for everyone.
I will actually say one more thing.
Oh, please,
If
yes.
none of that interested you, I'm not allowed 4 talks in a session. So we also do develop chemical reaction network exploration through machine learning, as well as doing machine learning on Hamiltonians. What don't we do? I honestly have no idea, to be honest. Like, so I can also talk to you about any of this stuff as well, if this is what you find interesting. Thank you very
cool.
much.
Wonderful. Thank you again. And I will wrap here with a couple of announcements. One, I just want to acknowledge one more time CMU Chemistry and CMU Materials Science and Engineering for their support of the symposium on an mini symposium. On an extremely related note, if you're joining us for dinner, we're going to meet just by the registration desk at around 6 to walk over. So it should give folks time if you want to go back to your lodging and drop things off, anything like that. Was that just a thumbs up, or did you want to add something? No. Okay, great. All right, that was 2 things. And third, just don't forget, starting in just about 10 minutes over in the other auditorium, we have the closing ceremony. So don't miss that last time to, soak in all of the wonderful JuliaCon vibes. Am I forgetting anything, Ray, Leticia? No? Okay, great. All right, thank you all again, and we'll see you around.